Okay, this is what you should be seeing. And just to give you guys a lay of the land, so here's Jupyter. Give it a sec. Also, if you have any VPNs or anything, get rid of all that crap, close out. There's a lot of WebSockets being done and a lot of weird ports opened up by Jupyter, and you will certainly have problems. So that's actually one of the cool things about doing this on a weekend, is that people are usually not at work and don't have that going on. But if you do have home VPN turned on to your company, try to get off that and just be as pure Wi-Fi as possible. Okay, so JC is good, everyone looks good. Okay, so you probably see this. If it asks you for, let's see, the username is root, and there is no password. So I'll type that into the chat here. Username root, no password. Just hit enter, get yourself in. So again, we're each able to use root because we each have our own GPU instance in Google. However, keep in mind that all I did on these GPU instances was start up Docker and pull down the like this workshop Docker image that has everything installed. So again, I highlight this because you could use this exact same Docker image, and you can like reproduce this on your own GPU cluster. So let me show you guys. If you go to PipelineAI, if you go to, close that out. If you go to docs over here in the upper right, you can go to the open source. You can actually, I have a community edition that's running a GPU. You can run some notebooks there. Don't go to that right now. Stick with this workshop. Here's all the other links. We do a monthly dev sync too. It's kind of fun. All the presentations, all the videos. But what you want to do is go to this open source and click into Pipeline. I'll share this link as well too. And this is where you can reproduce all of the fun stuff that I skipped over after that first section. But GPU ML, this is where all notebooks and code from this workshop live here. Boom. So I pasted it in there. You'll notice, so once you get in, actually I think there's probably going to be a couple notebooks open. That's just the way I had left the like Docker image when I burned it. Just do me a favor, just close all these tabs out. And so this is JupiterLab. Just real quick, JupiterLab is essentially a skin. It's much more advanced than a skin, but you can think of it this way, on top of the boring old Jupyter. And it's still using Jupyter Notebook, the server-side component, but it's completely rewritten. This is a pretty big project. There's a lot of support specifically from Bloomberg, and there's a lot of community support to make this thing really slick. And what's cool is, like with the old Jupyter, you had to open up a new tab for every like notebook. Each notebook had to open up in its own browser tab. Here, you could actually have side by side. You can, drag and drop and do all kinds of cool stuff. So I don't want to spend too much time on this, but because we have a lot to cover. But like, just know that I've been using this for about a year, and it's still termed alpha. If you look at the help about, actually, I think they're up to even 0.30 now. But it's actually pretty stable, and it was supposed to come out. There was a Jupyter conference a couple months ago in New York that I went to. It was supposed to become GA or like a 1.0 then. They wanted to get a lot of feedback from that conference, so it'll be early next year when they. One quick navigational thing about this environment is the left side here is this like slider thing. This slider thing only goes so far to the left. It'll go all the way to the right, but it doesn't go all the way to the left. and it takes up a lot of real estate. I almost abandoned JupiterLab when I was working with this because it was annoying. But I found if you click this files thing, if you click that tab, once, twice, it'll open and close like an accordion. So that'll give you some more real estate. If you notice some of these have green, that means that they're running. If you click on the running, so like just do me a favor and just click shut down on all 5 or 6 of these. This way there's no, we're all starting from scratch. You can look at other stuff. If you really insist on using the old Jupyter, you can actually get to it. You would click Launch Classic Notebook. I wouldn't do that. Stick with us so that we're all in the same environment. But if it's driving you crazy, you can certainly do that. One thing we will be using is new and then terminal. So just make sure you could do that. And do a ls or who am I and your root and all that stuff. So this is your own Docker container running on your own GPU instance, a full GPU instance with 4 CPUs, 30 gigs of RAM, I believe, and the GPU. So let's see. If you want to do rm slash, right, like recursive and just delete everything, that's fine. But you're not hurting anyone but yourself. So if you want to do some Bitcoin mining, that's totally up to you. But I'm going to kill all these instances when we're finished. So you can certainly save. What's cool too about JupiterLab is that you can actually highlight a bunch and do download. But I'm going to save you guys the pain of doing that and just show you that the exact same notebooks are available off of GitHub. So let me undo the highlight there. And if that link that I pasted in there, notebooks tab here, or yeah, the notebooks folder, these are all the exact same. So you can grab them from here if you want, or you can grab them from here. Also, GPU-ML, the README clicks you to a page here that'll tell you how to get things going. Click here to deploy. This is actually the Docker image that we're using, or these are the instructions on how to get the Docker. So this is exactly what I did for you guys this morning before you called in. Was I script this so that it starts in Google Cloud and spins up a bunch of instances. So, all right. These are all the ports that need to be opened for the WebSockets and for Jupyter Hub and for TensorBoard and all that kind of stuff. All right, so let's shut down that terminal. So once again, make sure that there's nothing in this running tab, and let's go to the first tab, or the first notebook, and just run this. So here we're just exploring our environment. If I do need to push out a hotfix, which I haven't in the year that I've been doing this workshop, but if there is anything that we need to change, I'll just have you guys rerun. I'll push it to GitHub and then have you guys rerun it. You'll notice this is a magic script that I created. Also in Jupyter, %% bash means give me this, run the following command or the following set of commands in a bash shell behind the scenes. It's kind of given to you for free by Jupyter, which is cool. Also, there's the shortcut, which is bang, the exclamation point, and it says run just this single line. So %%, these are called magics. PipelineAI is actually, we're building pipeline-specific magics for model deployment and model management and that kind of thing. Right now, we just have a command line, so we actually have to do, bang. But this is actually just a standard Linux thing, which is which, W-H-I-C-H. If you do which, you can see where this script is that I created. I hate when I take training classes and people have all these crazy scripts and I don't know what they do. So I'm going to show you guys how to look at it. That's the actual script itself. It's just doing a git pull, essentially, and trying to overwrite anything locally that's changed. You will not have changes to these to these notebooks that you'll want to save. I mean, you certainly can save them, but just know that we're pretty much just going to run through and explain everything. And there's not much time to give you a half hour to try to figure something out. And we just go through everything. So don't worry about saving these things. They're all in GitHub. Also, since you caught wind of this script, you probably want to know some other scripts that are out there. This root script is on the path and we'll hit all of these today pretty much. That's the one that we just ran. We'll hit these other ones as we go through. Also know that there's a percent HTML magic within Python, or within Jupyter that not a lot of people take advantage of. This is where you can actually render, live like Grafana dashboards and things like that inside here. So you could, like you can imagine where you would do %% pipeline deploy, and then go here % pipeline monitor, and it'll show that deployment and how the experiment is running, similar to those screenshots I was showing earlier. There's links to the meetup. Please join that. For a sanity check, just make sure this runs and it displays your IP. This is my IP, so don't steal that. In fact, I'm going to clear that output so you don't grab it. I have it masked up here in the DNS, local DNS mapping, host file mapping. Also, you can, oh yeah, actually this won't work, so don't worry about that because we didn't allocate IPs this way. Okay, so close that out. Oh, also, if you're having problems running this, the stuff's okay. Where are the stuff to kill to start from scratch? Yes. So if you're not seeing anything showing up here, like a little asterisk and a number, that means your kernel is shut down somehow, which was likely when we went and we shut them down over here, it got into a confused state. So if I shut down here and then try to run this, it's not going to do anything. It's going to look like it's hanging. This little circle here is the restart kernel. This is going to save you for the rest of the day. So anytime that you get into a funky situation, like no matter where you're at inside of this notebook, what you've done inside of it, just click restart, and then you'll be good to go. Usually I go over here and I'll kill everything because, again, at some point your GPU will get wedged and you won't be able to progress. So you'll have to kill. That'll free up the GPU. And then any future notebooks, you'll likely need to run this little restart kernel. Okay, so let's go to the second notebook, Explore GPU. This is the happiest moment in GPU, sysadmin, DevOps, AI ops, whatever you want to call it. This is the happiest moment of their life when they can run Nvidia SMI, which to me is short for smile. This shows up, you see everything, you see the temperature. That's always a fun one. Although I always have to convert to Fahrenheit to really understand where it's at. And there's some power, and here's your memory usage. So we'll be keeping an eye. This is, these are 12 gigs of RAM, these GPUs. The new P100s and Volta V100s have 16 gigs. For the data center versions, I think they're crippled a bit on the consumer version, down to 12. We're running the K80s, which is the most common deployed in the cloud across both Amazon and within Google. Google just announced the P100s. Amazon just announced V100, which is the latest. Google will be coming out with V100s early next year, sometime, hopefully. But when we run our code, we'll be looking at this and watching this thing blip and watch the GPU utilization go up as well, too. This gives us confidence that we're actually doing something. Do me a favor, run this as a sanity check. This just makes sure that we got placed on the right instance and the right CPU as well, too. So one thing to point out, this is a custom built from source TensorFlow version. And yes, while I know that bothers some people because of the reproducibility aspects and that, this is the only way to surface these little nuggets of like TensorFlow C++ goodness. Some of these optimization rally techniques is to build it from source. And right now, this particular version is commingled with some pipeline stuff, so it's not 100% reusable, but we are working to build and maintain. Now, if you do feel like building from source, let me show you this little trick here. CI, continuous integration.tensorflow.org, this is their entire public Jenkins build. And if you're looking for a particular build, so you click on TensorFlow over here, there's usually a lot more going on here. If you want to get the GPU version or a Python 3 version or the default or Android version, Mac. This is like down to the most latest builds. While I don't pull these specifically, what I do is I click in, find the most recently successful build. This is when I'm preparing a Docker image, with these optimizations for this workshop or for a customer, something like that. And I go in and see what's changed. So for example, they're now up to CUDA 9 and cuDNN 7. And this is because TensorFlow 1.5 is now supporting CUDA 9 and cuDNN 7. And there's a lot of really goofy parameters that show up that are not very well documented or that don't keep up with the documentation. And this is the true source. If you know that their Jenkins build is building, then this is where you go to look to see what parameters they're setting. So there's a bit of magic in here. They have these goofy install scripts, but at the end of the day, you can kind of like reverse engineer and figure out. The cool thing, this is the thing to highlight here. Let me zoom in. There's a tailspin here. Try to figure out what I've been. These are the goodies that you get when you build from source. You can turn on some faster malloc. Right here. Let me figure out what's going on here. Oh, I think it's the Zoom. The Zoom recording is actually taking up quite a bit. Google Drive. Let me kill that. All right. So these are the goodies here. You could also turn on Google Cloud Platform support, HDFS support. They just added Amazon S3 support. One thing that we turn on that is not turned on here in this particular build is this XLA stuff, which is experimental, but we have it fully working here today, and we'll be going through it. Is this the GDR? Is this the privacy stuff, I think, maybe? I just noticed that. Verbs, OpenCL. Here you can specify CUDA version. So again, they're up to 9, cuDNN 7. A couple other things. Do you want to use Intel's MKL? Yes or no? Android support. So, some non-standard type things, but that's where you can go to look at the parameters that are actually being used. Okay, so I think we're going to skip the CUDA stuff, but let me just show you guys what's going on. I'll talk about this actually in a slide. So you know what? I'll cover this in a slide. Let's skip Explore GPU for right now, and just as long as we can get to those two things, we'll be good to go later. One thing I do want to show from Python standpoint, there's this library called Numba that not a lot of people know about. So this is from Continuum Analytics, the folks that do Anaconda, you can actually, this is a drop-in replacement for NumPy that instead of NumPy being backed by C kernels, which is awesome, this is NumPy being backed by GPU kernels. So still written in C, but now works for the GPU. So if there's ever a time when a GPU kernel exists for like an operation that you're trying to do in Python, it will actually switch over to the GPU version. So it's pretty cool. This is all you have to do to decorate your code. You can turn on just-in-time compiling. You say device is true. So device is a CUDA term. Device is the actual GPU. When you hear CUDA developers talk about host, host is the CPU. So these are very, very overloaded terms. The term kernel is very overloaded, but kernel is the actual code that runs on the GPU. Let me show one thing actually in the previous, so I'm back at 01A Explorer. Let me just show you guys the code here. So here's C code. This is the CUDA code that we're going to run. You could run it maybe at the next break or whatever. But this is a kernel invocation, a GPU kernel invocation. And you notice that we're doing malloc on the host, so that's on the CPU side. And then we're doing a CUDA malloc with some error checking, because this is a pretty barbaric C code that's defensive and always like assuming errors and that kind of thing. So it's doing CUDA malloc on that device to hold these things. We're going to add up two vectors. And here we're going to do a mem copy from the CPU to that GPU, and then we're going to ask the GPU to do to run this like kernel, this GPU kernel. And this is syntax, so this is C++. This is like an overloaded operator. So like CUDA is mostly C++ 2011 like compliance, but also adds this special syntax for kernel execution. And this is just kind of CUDA terms here: grid size, block size, has to do with the number of threads. But what we're actually invoking is this kernel right here. Okay, so this is the code, and all it's doing is just adding two elements, but it's doing it at massive scale across the entire GPU, across all 5,000 cores, for example. So this is the highlight of the CUDA section here, is you write a very simple function called a kernel, and you have to do the memory allocation yourself, and you invoke it this way. Now, the way that this works is TensorFlow sits on top of cuDNN, which is a CUDA-specific library that sits on top of CUDA. So there's the GPU, which is the lowest level. There's CUDA, that is like the driver to talk to the GPU, or the library, the application library. And then on top of that is cuDNN, which is the neural network version. So that's exposing 3x3 convolutions and like matrix multiplication, all the common stuff. And then on top of that is TensorFlow and Theano and Caffe and that kind of thing. So again, this is an area that the TensorFlow folks determined is not to their advantage to focus on. So they're just reusing cuDNN, which uses CUDA. For TPUs, they are building all of these libraries from scratch, which they have not yet released publicly. Okay. When you run this is actually running in sort of an async manner. You have to actually say, hey, synchronize and wait for the answer, and then continue on. And of course, it's defensively assumes that there's an error. If not, then everything succeeded. We move the memory back from the device to the host, from the GPU to the CPU, and then we compare and make sure everything looks good, because we ran it on the CPU also to compare to the GPU. And we freed up all the memory, and then we reset. So that's that. There's an advanced way of doing it, which back to the Numba stuff. So yeah, this is essentially doing that same thing. Here's that add kernel, but it's written in Python instead of C. And if you put CUDA-JIT, it will actually compile this and create a GPU kernel behind the covers. And from that point on, here's that same invocation, except instead of the arrow, arrow, arrow thing like that, it's just brackets. So here, there's a call out to that. And yeah, so check out Numba. Might give you a little bit of speed up. Again, setting up GPUs is a little bit tricky. Okay, let me go back to check if there's any questions. Let me go back to the slides. Okay, so everyone got your GPU there. Google Cloud, thank you. This time around, the other guys are going to get to you soon. We have everything running here. We got Oprah giving away her Christmas gift. This is my Christmas gift to you guys for the next couple hours. Verify everything. So we have TensorBoard, we have Spark. We're not going to get to any Spark today, but if you do get this set up on your own, you can actually run a Spark job to do ETL, to do feature engineering, and write it to HDFS, which is also running within this Docker image. Oops. If you you go back to your that main page, there'll be the link to HDFS. If you click on that, you'll get this green Hadoop thing here, and you can actually look at what's in HDFS and see. And so TensorFlow now supports HDFS, which is really nice. Yeah, actually has since earlier in the year. Yeah, anything, if you see any errors, stay calm. We'll get through it. Either post it in the chat or we'll all hit it at the same time, most likely. So that's how you get to the terminal. We just did that Explore environment. We did this. Getting GPUs to work on its own is very difficult. Getting it to work through Docker is somewhat difficult, made easier by the Nvidia-Docker project by the Nvidia folks that wraps the GPUs and exposes them, pokes a hole through the Docker container and treats them like mounts. And then if you're trying to use Kubernetes with Docker, with GPUs, this is pretty much near impossible to reproduce you with the operating system, with the version of the kernel, the version of TensorFlow. There's like so many different versions that come into play. If you are trying to reproduce a blog post that you've seen that has this working, it's very likely that if it's more than a few days old, that that blog post was using a kernel. Even on the same cloud provider, Amazon is always updating the default, like Ubuntu kernel, for example, cause incompatibilities with the current CUDA drivers and things like that. So yeah, this is kind of visually what I was saying before. So it's actually kind of reversed. At the lowest level is Ubuntu and the kernel, and then you have the Nvidia driver, CUDA, cuDNN, and you would pip install or build from scratch these, yeah, like these various libraries here. Okay, one thing to point out, there's GPU half precision. This was a huge deal this week at NIPS. Everyone was talking about it. A lot of research going in. So half precision is floating point 16. So think of this as just lopping off the last 16 bits of your mantissa. And this is actually okay for deep learning use cases. This is becoming more and more common to lower the precision, even at training time, and especially at training time, because you can get through and train your data set literally twice as fast. So in the left here is a comparison, single precision to half precision on the, let's just focus on the Pascal P100. It's literally, because yeah, half precision wasn't supported before P100. So this is built into the hardware where two floating point 16s can now fit into one floating point 32 GPU core. So this is huge. So this is an instant 2x speed up. And what this lets you do is for the same amount of data for your fixed data set, you can get through it twice as fast, meaning you can try out different hyperparameters. You can start to learn your data. You can learn the model. You can start to gain the intuition twice as fast as you could at 32-bit. Now, you will end up, because your final accuracy of your model really is dependent on the precision of or the number of bits, right? The more bits you have to represent and to hold these floats that you're learning, these weights that you're learning, the more the overall accuracy will go up. And so, but at the same time, when you're starting off and you're still learning your model, you have to, really play with these knobs quite a bit, or these offline hyperparameters. So you can get through them twice as fast. Then once you start to get the intuition, then you can back into the full floating point 32 precision, and run it for 2 weeks instead of 1 week, or 2 days instead of 1 day. So remember here that in these neural networks, the network is what matters, right? The way that these neurons are connected, the architecture, this is a hyperparameter, right? So one thing people do, it's not just change learning rates and change, tree depth or whatever, but it's for like neural networks, one of the hyperparameters is how these nodes connect to each other. And there's things like dropout, where you can snip 50% of the connections, during the training process, sort of stochastically, right? Like randomly, just not follow the same path through the network that it did before during training. So what you're trying to do is introduce right, like enough noise to so that the network doesn't learn patterns that it shouldn't learn, and it stays focused on the actual true data. And yeah, supported by Pascal P100. Volta V100 actually supports floating point 16 and a couple other cool things here that I'll talk about in a sec. Yeah, so Volta, the V100, which came out this year, actually the consumer version was just announced at NIPS just a couple days ago. It's a $3,000 card. It's very, very similar to the data center version, which is not normal for the NVIDIA folks. They typically cripple the consumer version to the point where it forces you to, think, if I'm using this for something commercial, I probably should go with the data center version. But the consumer version, I believe the main difference is it just has 12 gig versus 16 gig. In terms of cores and number of streaming multiprocessors, which is a term CUDA people use, that's kind of a collection of cores, is the same. And also this Volta V100 has these tensor cores, which are very similar to the Google TPUs. So they have 5,300 of the generic floating point 32 GPU cores, but they also have 670 of these tensor cores, which are highly optimized for this particular calculation in the middle there, which is 2 floating point 16s. So 2 matrices being multiplied, and then a floating point 32 add. So what we're doing is we're actually mixing precision here. So because the 2 matrices on the very first part being multiplied, if you can get 2 floating point 32s down to floating point 16, it's way faster to multiply 2 16-bit matrices than it is 2 floating point 32, especially when you can pipeline 2 floating point 16s onto a single GPU core, 32-bit GPU core. The one tip here, empirically, the matrix dimensions should be a multiple of 8. This has to do with the way CUDA strides and performs these operations down at the hardware level. Multiples of 8 will always dominate if you're comparing it to 10 or to 12 bit, something like that. Always do, or 12, multiples of 12. So if you stick with 8, you're in good shape. And then also the ability to mix and match. So we have 2 floating point 16s and then adding a floating point 32. Yes, if you notice, this is a very common thing to do in a neural network, right? Because we're always multiplying 2 things together and then adding. Even down, in simplest linear regression, we're doing, matrix W times X and then adding in the B bias. There's just another look at floating point 16 and floating point 32. Here's a quick, so this is actually some benchmarks that were done by a friend of mine, floating point 32 versus floating point 16 on Amazon. And one thing that was interesting, and he actually used the new P3, which is the Volta, and used the G3, which is an older Tesla, and the P2, which is the K80, which is what we're actually using today, but on the Google side. And here, floating point 16, if you drop down to half precision, you can actually get much more than a 2x speed up. And there's still some discussion on why it's not a linear 2x speed up because of the that ability to put 2 floating point 16s into. We believe this is also related to the tensor core speed up. But not exactly sure. There's a blog post on this too. I can try to dig up here in a sec at the next break. Okay, so what about Google Cloud? So this was Amazon. Supports K80s, the P100, the TPUs are where this is going to be in the future for Google. They have a lot of software being built around this. There's extensions to TensorFlow that are starting to creep into the API that are specific to TPUs, and people are speculating like why that is and looking at the code. And also Volta V100 I hear will be coming soon. Yes, Amazon skipped the Pascal P100 and went straight to the Volta V100. And you can attach, so what's cool about Google Cloud is you can actually provision a CPU instance and then attach a GPU to it. So of course, because these GPUs live on separate boards elsewhere in the rack, there's going to be a bit more latency between the CPU and the GPU because it's physically not on the same board, like the same motherboard. But so that was always kind of cool. And then I noticed that like Amazon has something similar. It's called the Elastic GPU. I don't quite understand how it works. It only works with certain GPU types and CPU types, and I just kind of gave up and either use their full P3 Volta V100s or just use Google Cloud. All right, I'm going to skip some of this. It's more about cuDNN. CUDA's barbaric. This I do want to emphasize. CUDA streams. So I mentioned in the code earlier that when you do an operation, so like before streams existed, the GPU could either be doing compute, where it's actually doing matrix multiplies, or it could be loading in data. Yes, obviously that's not ideal. What you want is some sort of interleaving, right, that's happening. You want data to be coming in, keep this GPU fully saturated, right? Keep the utilization as high as possible. It's very rare to see like GPU utilization, go above 30, 40%, at peak when you're like really, really hammering it. We'll talk about ways to improve that and to profile it, and some ways there's some new APIs within TensorFlow called Dataset API that are much more optimized and much more low level. C++. You can use them at the Python level, but it's just dropping into the C++ to do parallel transfers and more optimized like data movement. So the key here is that they're like overlapping compute and I/O. This is heavily utilized by TensorFlow in what was formerly there, or still is, but the first generation is called Qs. The second generation data movement library is called Dataset. So it's starting to, what you're seeing is TensorFlow is realizing that the bottlenecks are really how people get data in to TensorFlow, and especially onto these GPUs. And at the same time, we're seeing the Spark folks, the Databricks folks, renaming their Spark Summit to the Spark and AI Summit, for example, which they just announced last week. And Spark itself is going through a bit of a transformation, or kind of an identity crisis, if you will, to be more AI friendly. Right now, Spark is starting to slowly get lumped into Hadoop. And like Databricks does not want that at all. They need to keep selling their product. They need to add in. So they're targeting with their ML lib project, or the Spark ML. They're starting to add in more first class image transfer. Yeah, it's these image transformers, image classifiers. They have full support for the inception model. And they're starting to come out with more and more demos, and starting to see more Spark, people popping up at conferences and things like that. They're a bit behind, and I feel like TensorFlow will be able to creep into the ETL territory, or the feature engineering territory, a lot quicker, than these Databricks folks trying to get more into AI. It's not an intelligence thing at all. It's just it's a scale thing. Down to the number of GitHub stars. There's 80, 90,000 GitHub stars on TensorFlow. There's a ton of commits coming in around this stuff. Google is very focused on making the ETL process a lot easier, so that they can push you more into TensorFlow, so they can push you more towards their Google Cloud product. Shared memory, I'm not going to spend too much time here, but the old days of the code I showed where we were moving memory to and from CPU and the device, that GPU, with more modern CUDA libraries and more modern processor, or these GPUs, you can actually just refer to the memory, and the underlying Rally drivers will actually take care of the GPU page faults and then migrating it in, and maintains like heuristics. If you're using the same CPU memory a lot, it'll just move those buffers over. Sometimes it's faster just to access, you know, like one time, and not physically move that data over. So yeah, there's a lot of innovation going in on. The first generation of CUDA's unified memory was pretty sloppy and not very efficient. They just got something out, and now they're actually doing a really good job. So these notebooks we already saw. Keep going. So TensorFlow. This is not really an intro to TensorFlow, but I do want to set some of these terms straight. Tensors, these things are flowing. Tensors, n-dimensional arrays. Scalars, vectors, matrices are all forms of tensors. The term operation, so I mentioned this earlier in the context of there having to be a C++ version or a GPU, or either a CPU kernel that's written in C or a GPU kernel that's written in C that has to back all of these different TensorFlow operations. So everything that we're doing within Python is just literally calling into the C version or the CPU version or the GPU version. Similar to Numba, which if you're using NumPy is calling the CPU version. If you're using GPU, or if you're using Numba, it's calling into the GPU kernel. So there's other types of operations besides numerical. There's things like summary writers. This is actually collecting up all of your metrics that you're maintaining during the training process. So this is one cool thing about TensorFlow is it really encourages insights during model training, and it stores it into a directory, and it's essentially just a bunch of log files that TensorBoard knows how to read. And it's a fixed file format, and you know, it's a proprietary format. Well, this is all open source, but it's a format that is not similar to Parquet or anything that like we're used to. It's called these event files, I believe they're called, and TensorBoard can just read these and then show charts of how you're and you choose which scalars or which histograms or which things that you actually log, and the frequency of which you choose to log them. So you don't want to log too much because you'll slow down training, but you want to log enough that you can catch when you're starting to overfit, or you start to see vanishing gradients or exploding gradients, things like that. So graphs. If you haven't picked this up by now, pretty much, right, yes, everything that we do ends up being a graph. Spark sort of brought this into the spotlight here for batch data processing, which is building up graphs of filters and maps and projections and joins and things like that. So similarly, we have a directed acyclic graph within TensorFlow that represents our neural network. Now on the right, this is actually what we're going to be using today, which is just linear regression. So there's no magic here. You could argue if this is even considered neural network, what the layers are, that kind of thing. But this still represents a graph. So there's inputs, which are on the bottom right. Those are in green. The W and B are the variables that we're training. So I'm kind of skipping ahead here. Tensors are in black. Those are the things that are flowing. We're fetching outputs. So, and here we're actually fetching from an operation, which is kind of odd. This actually took me a bit to grok, fully, which is so in the actual TensorFlow API, there's things called feeds and there's fetches. Feeds are the input, and fetches are what you're pulling out. So in our y equals wx plus b, it would y would be the output and x would be the input, and w and b are what we're learning during the training phase. So devices, again, this is hardware device, CPU, GPU, TPU, and session, similar to Spark. So I kind of skipped over that one. Session you create a TensorFlow session, and that's what you're operating with. And you can have multiple graphs actually within a session. Places I see multiple graphs are when people have a sort of feature engineering portion of their graph, which is doing data augmentation or like data generation, things like that, where they're taking a single image and they're cropping it, they're twisting it, they're like doing various transformations with that same label, right? So we're taking labeled data, we're going to augment it, create maybe five different variations of the original image, and show the network, right, like different views of that same image with that same label. So this is very powerful, especially when you're dealing with not so much data. And bottom right here, the way that, so I'd shown you guys a with statement before in Python, context manager they're called, which is, kind of a scoping thing. So anything that's indented within this with will inherit this device or series of devices. And this is just kind of, these variables and the graph, these are two separate things. And this is, I think the next slide, where do I talk about it? In a couple slides, I'll talk about it. But TensorFlow itself, so there's this concept of a graph, and that's literally just like a binary representation of nodes and edges, right? Of your like directed acyclic graph for your numerical computations or for your like data augmentation. Separately, inside of your session is stored these variables, and in a distributed context, these variables actually end up on a large cluster because we're learning millions of variables, right? These weights. And this huge cluster, these weights can't fit onto a single machine. It's beyond 4 terabytes or whatever the biggest nodes are now within Amazon, things like that. So these variables that's the stateful part of your model, right? When you train a model, you're constantly updating these variables, and then when you take a checkpoint, you then would take the current values of those variables and then dump them to disk. And the static part is the graph. Okay? And there are ways to use dynamic graphs and things like that. But for now, let's just consider the graph to be static. That's something that we define in code, very similar to Spark when we're creating joins and filters and things like that. And then separately are these variables. So these things travel together, like typically, but they can be pulled apart. So you can reuse someone's graph and throw away all the stuff that they've learned. Now that's not usually what you're doing. Typically you want both the graph and that like latest checkpoint, because that checkpoint contains all, has been trained on millions of like images, for example. So what you like typically do is you want to reuse those, retrain with your data, your specific images that are specific to your domain, but still reuse all of the weights. And weights are used at like different points within your graph. And instead of throwing all that away and starting from scratch, you want to build on top of that. Execution is lazy by default, similar to Spark. TensorFlow 1.4 introduced eager execution. This was a big differentiator between PyTorch and TensorFlow. Was in PyTorch you had kind of a REPL, where like a command line where you could just type in the code and see it being executed. That's really cool at research time and developing your model and testing. But when you actually go into production, you want something that can be optimized, right? Like a physical, right? Like a logical, like query plan down to a physical, right? Like execution plan. So with this eager execution stuff, that was really cool with PyTorch. PyTorch was generally not the best choice for production, serving models, which is the focus for Pipeline and focus for this workshop. So what's cool is that TensorFlow actually went the other way. They started off lazy, which is optimized for serving, and they then added eager execution to satisfy the researchers that preferred that style. That will likely become the default moving forward. it will become the default in terms of demos and examples that you see because it's more tangible. That was always one of the arguments about Spark. Is Spark, you had to kind of mentally picture how the flow of this program worked because it wasn't necessarily top down. Yes, as you're like reading the source code. So, and then, yeah, there's ways to like linearize execution. This is pretty advanced stuff, but by default, the short of this is by default, TensorFlow assumes that you have, 15, 16 workers, and it's spread across a cluster, and it's using distributed TensorFlow, and it has tons of memory in GPU. That's not always the case, and in fact, one thing that comes up all the time on Stack Overflow is people trying the GPU version of TensorFlow on a either commercial GPU that they, or consumer GPU that they have in their like Alienware, gaming box, or they're trying it on a cloud instance that they're trying to keep costs down. And what happens is that if you're in a really limited amount of RAM, like TensorFlow doesn't do a good job of like detecting that and changing its execution flow. So you have to do some hacking around, and yeah, I'll show you guys a GitHub repo to explore later, but you can actually convert TensorFlow for a particular training run to linearize and kind of serialize how it executes different operations. So by default, it's going to try to do as much in parallel as possible because that's where the scale comes, but that's not always the case. So here's some of the things to pay attention to. It's called operation parallelism. This is pretty advanced stuff here, but just know that there's like inter-op, so like between op. So here it says by default, TensorFlow is running multiple ops in parallel. This is when you have low core, small memory environments, you would set this to 1, basically. That would give you the linearization. Intra-op is within ops is dealing with threads. This is when you have compute bound, and it's reusing what's in RAM. This is where you would specify number of cores. So like you don't see people do this too often. It mainly comes up on these edge cases where people are using a framework like TensorFlow that is optimized for distributed, and they're using it in a very constrained, like low memory or low CPU environment, or it's low GPU environment. Let's see. So again, graph is separate from the variables. What's the other bullet point here on this one? So the graph, which is our y equals wx plus b. There's this other entity that travels with the graph, and combined they're called metagraph. It's this concept of like metadata, and metadata has specific assets that that need to be there for the graph to produce something human readable, for example, like something that's going to convert like the numeric classification of an image into the human readable term, like this building is a church, or this is a school, this is a bathroom, right? That human readable term is not needed inside the graph, but has to travel with the graph for times when this is being used for like model serving, right? Like things like that. So there's other various types of like assets as well too. You can actually stuff anything you want into this metadata thing. I've seen some people do some crazy things. And you can also tag models. This is very good for model management, that kind of stuff. Version your models. The other big thing is signature depth. So this will come up more when we talk about TensorFlow serving. But just know that internally, the names of these nodes, in particular the like input node X and the output node, which is an operation, which is add. So TensorFlow can actually name those something different than what you're naming them. So internally, TensorFlow can tack on :1 or :99 or some garbly-goop kind of thing. And you don't always know. From training run to training run, that could change. That's totally not a guarantee to be named the same thing between runs. What was happening was when Google Cloud ML was created, people were uploading models, and each run had different variable names, or like node names for the feeds and the fetch for the inputs and the outputs. And this was breaking a bunch of code, because when you first upload your model, you specify the input name, which would be x:0, the output name, which would be add:0, and then you train again, you upload, and the serving layer is expecting x:0 and add:0. And that's no longer the case. For like whatever reason, like TensorFlow named it something slightly different. So the signature def gives you the ability to do a like logical mapping, like mapping between the like logical name, which you can call anything. You can call it input, you can call it feed, you can call it x, to the physical name, which would be x:0 on the first run, x:99 on the second run. So the key here is that signature def is generated at the same time as the training, as that graph is being created. So that's super important to know, and again, follows this train to serve mentality, right? We're training these things with the intention to serve them. One term you should be familiar with is this term called freezing a model. When you freeze, you're physically, you take a checkpoint, you have these variables that are on disk. Here, we're only learning 2 variables, so it's kind of boring. You physically burn these in. So W and B now become 0.328 and -1.407. And now that you've frozen this, so this is the basis of a lot of post-training optimizations, is that you have a frozen model. And excuse me here. So once that model is frozen, it can no longer change. And so, yeah, I'll show something here in a bit where after TensorFlow trains this linear regression, the super simple model, that end state for that model is this huge graph, this huge, it's got like tons and tons of operations. I'm just going to cough here in a sec. Yeah, and so these, yeah, so like with linear like regressions, these 5 nodes turn into about 84 nodes. And that's certainly not suitable for serving. So freezing actually can go in and strip out all the unused stuff and then convert things, right, like these variables that are mutable change into, right, like non-mutable, the immutable, right, like constants. Okay, TensorFlow serving, this heavily relies on the save model format. And this is a somewhat newer format that's a little bit mysterious. It's a bit different than, well, it's very different than when you export a model. So when you export a model, like traditionally, you are essentially taking a snapshot. But the bundle that's exported is meant to be picked up by somebody else to continue training. So it contains all of the 84 nodes in what would normally be a 5-node, right, like linear, like regression model. And, but save model is one step further, and it's doing, you know, some of the stripping away. It's freezing the model, and it's really setting up the model for serving. And this concept is very confusing to people. I tend to like answer this quite a bit on Stack Overflow because I see it come up all the time, which is when do I use export? When do I use save model? And like that's the big difference is you would export if you don't intend to serve. And if you do intend to serve this model in production, you would want the save model. If you plan to continue to train, you would use export. And this hooks into the signature def process, forces you to define that. This like estimator API, which I haven't covered yet, very, very important, actually has a first-class method called export save model, which is unfortunate that it uses both export and save model, because that's extra confusing. It's the old style and the new style in the name, but it's actually exporting the new format. You can use the save model CLI binary that actually does come with the like pip install actually has this. you can actually inspect and look at, if someone hands you this model, if they're handing it over the wall in a traditional sense, you can inspect it and see what the signature depth is, for example. And then you, the person who's like productionizing this, right? So this is something Pipeline does like by default. When someone hands us their model, we actually have ways to inspect it, to grab the inputs, to confirm that this is the input, this is the output, and then we can package it up into Docker and then ship it out. So yeah, like keep an eye on that. Utility is really handy, especially when you're trying to figure out why your model's not exporting the things that you want it to. This model format's used by TensorFlow Serving, of course, and it's supposed to be the new standard export format, right? But again, there's still quite a bit of confusion and not much answers coming out of the Google community, the TensorFlow community. All right, batch norm I'm going to mention, but not spend too much time. In mini batch training, so stochastic mini batch gradient descent, the like mini batch part can you're pulling in like sort of randomized samples of data. So like imagine you have a bunch of images on disk. You want to shuffle those images, right, like initially, so that the network doesn't learn the order in which those images are stored on disk. That's not good. If it's not time series anyway, if you're using time series, then of course the order matters. You shuffle, you're now pulling in mini batches. And depending on how lucky you are, and by lucky, the most ideal situation is that you have an even distribution of the overall distribution of all of the images. You have an even distribution within that like mini batch, right? Like a consistent like distribution that is representative of the overall data set. When that doesn't happen, your model is sort of limited in its training ability, and it will start to make assumptions one way, if it's way to the right of like the standard distribution kind of thing, or and so with like batch normalization, every batch that comes in, we're slowly learning the like overall mean and variance. And so this is super powerful. And actually this week at NIPS, there's a concept called batch renormalization, and so which actually does exist within TensorFlow. I believe it's just another flag on batch normalization. You would say renorm equals true or something. It's very subtle, but with just this like straight up traditional batch norm, what you're doing is maintaining kind of a moving average, if you will, of the overall mean and the overall variance per layer. And what that lets you do is when you get in a new distribution for your mini batch, you can subtract out the most current mean and variance that we've seen globally, right? So like we can basically, for each batch, we can adjust based on what we think is the overall distribution. So let's see. Yeah, TensorFlow is on second generation, I think, and it's actually the third generation now with this batch renormalization. You can also, so you can fuse these layers together, which is nice, and especially at serving time when, yeah, so things that you do at training have to be reproduced in some way at serving. So things like batch normalization, things like dropout, right? Like these things have to be adjusted for when you go to predict, and really just do that forward propagation. And so this is where some of these post-training techniques come in, where you can fuse together any extra things that are required for, right, like adjusting for the batch norm or for the dropout. You can do things once and burn them into the model, essentially, freeze them into the model. So dropout here, this is, yeah, obviously a very popular technique, paper in 2014. What you're doing is you're just sort of randomly, typically people use 50%, which seems pretty high, but what you're doing is you're impeding you're not letting like you're sort of always introducing more and more randomness, right? And so each training pass through, if we snip 50% of our connections, each time through, the network is being crippled in some way, or it's it's being forced to learn something new about the data that's coming in. And so this prevents, right, like local minima, sort of getting stuck in this local minima. This prevents things like overfitting to a specific data set. So yeah, things like this stochasticity and this randomness of these neural networks, these things are like very much celebrated. A couple of people to pay attention to, this guy Yaroslav, he's my neighbor in San Francisco. I saw him this week at NIPS. He's got that like linearized thing. This is pretty low level stuff here. He actually calls it stuff. This is all TensorFlow. It's a lot of benchmarking and a lot of him tearing or like diving deeper into the Python APIs to get to the C code, showing ways to optimize under certain conditions like low memory GPUs, single GPUs, things like that. Also, this other person, Derek, I think it's Derek Murray, Douglas Murray? No, yeah, he was an old hockey player. Derek Murray. He works on TensorFlow, and he's become Mr. Dataset. I don't think he, probably realizes this or wants to be Mr. Dataset, but he's done quite a lot of work on the TensorFlow Dataset API. So keep an eye out for him. I actually stalk or follow these people on Stack Overflow. There's a way to follow a specific user's activity. And so each morning I see which problems they've answered. And typically they're problems that I either have seen but didn't know what was going on, or it's something I still haven't hit. And so I pay very close attention to these guys because they have the answers right away because they know this code very well. So Yaroslav went to OpenAI for a bit. He's now on his own, and Derek is still over at Google. All right, quick slide on if you need to integrate with your existing Spark or Hadoop, you can use some of these libraries, Ecosystem Project, and what's this? Training, the big takeaway for this is GPUs, while we can keep adding more and more GPUs, and we can make GPUs faster and faster, if we can't get data to the GPUs, to these much faster GPUs, we're still limited. It's just adding more like GPUs that is going to lower the overall saturation of our GPU cluster. So scaling them up or out doesn't really help. They are classically underutilized. In fact, CPUs are classically underutilized. And in fact, there was a cool talk this week I saw where so the Nvidia folks are working on ways to reuse, so through TensorFlow, of course, and Torch, but ways where the GPU can. So think of the data pipeline, right? Coming in. So if there's data augmentation going on or data cropping, this stuff is classically done by large CPU clusters because, these calculations aren't that complex. We want our GPU to be focused on back propagating and, matrix multiplies and not just, cropping and, simple shading and things like that. So, but because these GPUs are so heavily underutilized because of slower pipelines and, there's just natural limits to how fast you can get data off of HDFS, onto the GPU. So, ways to use some of the GPU's memory and this underutilization of the GPUs to help out in, cases where that GPU has sort of leftover compute, right? So it's kind of a weird thing because, you're sort of using the target device for a reason to speed up getting data into that target device. But so yeah, it's a bit of a recursion thing there. But that bottom right chart's kind of interesting because this is showing, with the Tesla K80, which is what we're using, the input processing. So yeah, so right, what's happening is there's starting to become more and more hardware that's being built for TensorFlow specifically, actually, and for neural networks, right? These GPUs were built for texture rendering and graphics processing and things like that, not necessarily matrix multiplies, certainly not for half precision. And they're even going down into 8-bit precision, 4-bit precision, I heard this week. There's some research going on within Microsoft to do 7-bit precision. Each bit that you drop can speed things up, both training and serving, because when you're training, of course, you're doing a forward pop, right, like propagation, which is what you're doing for the prediction, but you're also then backpropping and like assigning error to each node and layer that was participating in this forward prop. Yeah, these accelerators will get faster and faster, but the speed at which you can pull data off of HDFS, and the speed of your like network and things like that is not getting faster. So it's a bit of right, yeah, it's like optimizing kind of the end of the chain, but really the big things that you can do to get data in through the pipeline faster are use this new dataset API. Really take a look, if you're using Amazon, make sure that your nodes are in placement groups. For example, this makes sure that your nodes are in the same rack on a data center, for example. I don't think they say it that way specifically, but it's putting nodes as close together as possible, because we're telling Amazon that these are going to participate in, the same workload. And yeah, and then just faster networks. So things like the InfiniBand and RDMA and things like that. So these have been contributions from the community. So people like Facebook, people like Intel. I believe it was Yahoo that has a paper on using Spark with TensorFlow, and they optimize their distribution and their like network communication by using RDMA, which is much. It's different than gRPC, which is what TensorFlow uses out of the box and is much preferred by Google, because that's what they do everything is with gRPC. But if you can use a much faster network and a very highly optimized protocol for these types of workloads, then that's where the big gains will come from, and then hopefully we can match. So yeah, and then the bottom right shows Volta V100, which is 10 times faster than the K80, but we're just saturating it even less. Big takeaway here: don't use feed dicts. This is in a lot of the sample code. This reminds me of the Spark collect method, when you would grab someone, like a demo off of the Databricks site or the Spark site, you would run it. You wanted to run collect because you wanted to just make sure that the answer was being calculated across this cluster. The problem is collect actually is the worst thing you can do in Spark, where it pulls all the data from all the nodes, shuffles it, brings it down to a single node, which is where you're running your controller Spark app, and that causes all kinds of problems. So, but you see it so often that you mentally think it's okay. So this is similar with feed dict. Feed dict is a way to is a Python specific way. It's a parameter that you pass to your session run command, and it's essentially, think of it like a big hash map. And the problem is it's being pickled between Python and C++. It's being serialized, and this is all the classic stuff that we saw with Python and PySpark. Right, so the initial early versions of PySpark did exactly this, where they were converting Python objects, they were pickling them and serializing them to the JVM. Then the JVM had to recreate the objects in memory and then do all the computations. In more modern versions of Spark, after I believe Spark 1.2, 1.3, the Python layer is literally just building up that DAG, that execution graph. And that's what's being passed into the JVM. It's just this tiny like representation, similar to the like TensorFlow graph that I spoke of before, where the graph is static, the variables are what we're training. So yeah, so back to feed-dict, not optimized for like production pipelines. It's single-threaded. It is doing everything synchronously, which is bad. There's one thread that is pulling data, for example, from HDFS and presenting it, and then once it's taken, then it goes back and pulls in like the next. So this is very bad for saturation and for gaining high CPU GPU utilization. So the suggestion is to use queues. Are a bit complex, and they work pretty well. They just require you to know a lot about threading and think about thread pools and capacity planning and batch sizes, and you really have to do a lot of profiling even with these queues. They get you closer because they're more native, and they have C++ operations that are backing them. So they're much better than feed-dict, but the dataset API is really where you want to be. That's what's going to have. Yeah, so check out this performance tab is where I spent a lot of time when I was preparing these slides, is in that performance tab. So here's a way to profile. If you just do a couple lines, here it's a bit sloppy, non-intuitive really, but this is a way to generate something that can be profiled. So what's happening here is I can slip this code into my training job, and out comes a view. So the way it's actually using the Google Web Tracing Framework beneath the covers. There's a Chrome plugin that can render this. This is moving into TensorBoard, by the way. So with a similar type of like boilerplate code in your TensorFlow job, you can actually generate something that will render very similar to this inside of TensorBoard and show you where time is being spent, right down to like the operation name. And so like one thing to note, because I'm going to compare this here in a sec to a better way of doing this, there's about 15, 20 operations going on in here. So like this is different than linear regression. This is like a more complex network, but there's a whole ton of stuff happening on this GPU, and these are separate operations. And you'll see memcopy. There's memcopies here. There's a memcopy here. There's memcopy. So there's what we're trying to do is to reduce memcopy, because what I had shown with the CUDA code is that's the slow part. If you notice, there's these streams, right? So this is the advanced version that I had talked about. Like we didn't actually look at the code, but the code's in there inside the second or third notebook. But these are the CUDA streams. And so CUDA streams are what's doing that like interleaving, right? And it's letting us do some compute and some, right, like data. So here's the memcopy. We see this stream 13 is doing that memcopy, and there's some other stuff going on in like different streams and that kind of stuff. So that's where TensorFlow is. So like TensorFlow is 3 or 4 layers above the GPU, but it's so this is where we could see operations that are using the GPU. Okay, so queues, I'm not going to talk too much about these because I think dataset's where it's at, but it's essentially, these are definitely using CUDA streams. Here's what I was talking about before. You have files on disk, then you randomly shuffle them so that we don't learn the order. They're then presented. So there's a lot of stuff going on here before you even, and so this queue is where my TensorFlow code would pull from. And so think of queues less as computer science queue and think of it more like a pipeline. These queues are just nodes inside of your pipeline. And you can build your own custom queues, but out of the box, it comes with a random shuffling queue and common things like that. You can pull from S3 and Google Storage. I know of people, so like we actually have a Kafka version. We haven't open sourced it yet because we're going to switch over to the dataset API, but we can pull from Kafka similar to how we're pulling off HDFS. Let's see, cropping, shuffling. Also, the classic problem of the small files. So TensorFlow has its preferred file format, which is called TF record. And so as we know about this sort of explosion of file formats over the last few years, is these file formats are like optimized for a particular workload. So things like Avro, things like Parquet, things like Orc, right? Like these are, those were like optimized for batch, right? Like aggregations and, you know, columnar sums. And so physically they're taking advantage of the fact that they're storing data next to each other on disk or in memory that will be used together as part of some like operation. So similarly, TF record has an optimized file format that's like optimized for like pipelining a bunch of data together and like lowering, you know, disk seek and like yeah, it's like memory seeks and things like L1 cache, L2 cache, things like that. So these queues typically use CPUs to free, if you have to make a decision, you know, if you have a cluster of CPUs and a cluster of GPUs, you would typically use the CPUs for these queues or for this pre-processing. So like I had just mentioned, there's some like research going on to actually, while the GPU is sitting around waiting, it can actually participate in this pre-compute, this like data augmentation step. And then once that data becomes available, then it participates in the training. So yeah, the overall goal is to saturate these things. One thing to mention, this is specific to queues, but also something to keep in mind is when you're just like, well, yeah, like this is not specific to queues actually. This is thinking about the batch size. So batch size came up quite a bit this week at NIPS as well. Like traditionally, you would want, you know, 64, 32 for a batch size, something like around there. Now there's this push towards larger batch sizes, towards right like 8,000, right like 8K. So think of like these images, right? And but physically, you will be limited by GPU RAM. So if you want to operate on a batch, you have to think about how much RAM you have. If you have 12 gig and your average like JPEG that you're working with on disk, you know, is, I don't know, right, like 100K, something like that. You would then divide into the amount of RAM that you have, and what comes out of that is the number of like JPEGs that you can operate on that will fit into GPU RAM. But now keep in mind that the real value, the real number comes in lower than that because you have temporary variables being created, you know, from the like dot products happening, from the like partial derivatives being created. So there's things going on inside this GPU like that is needed. There's RAM that's needed that's beyond just storing the JPEGs that are being currently operated on. This is some of the nastiness of the queue stuff about number of processing threads and queue capacity. Queue capacity is the number of batches. So, you know, the like magic number tends to come in at 5 as like an empirical. You want, you know, to smooth out like batches that can be right, like processed quicker. So let's say the GPU gets a bunch of blank images and it can just rip through that right, like right away. And then now it's like waiting for that next batch. So by saying 5, like we can kind of smooth out, you know, peaks and valleys of processing time. 5 is always kind of a good number. 5 actually comes up quite a bit with Spark when you're trying to figure out the number of partitions. You have a data set and there's this magic number of partitions, a number of nodes that you need across the cluster to operate on this data set. And what you typically do is calculate based on the number of right, like CPUs that you have, cores that you have, you would typically multiply by 4 or 5. And that's how many partitions. And the thinking there is that you are oversubscribing because you're typically I/O bound. And, you know, while I/O is happening, you want these CPUs to, you know, like still be crunching and that kind of thing. Let's see. Yeah, dataset API. So this is the new like evolution of the Q stuff. Here's where we have maps, and we can use Python generators, which is really cool. So yeah, everyone loves Python generators. Pretty slick. You can convert into tensors and out of tensors. This is handy when you're, well, yeah, I mean, this is just how you would like operate on these things within TensorFlow. There's these iterators. So, you know, there's data set, and there's, you know, 3 different kind of main versions. TF record, we already talked about. Fixed length is, yes, obviously what it like looks like, it sounds like, and there's text, and this is for like CSVs and things like that. You would then instantiate this iterator. You know, these are very basic like primitives here, and there's a one-shot iterator, which is what we're probably used to, where you can't start at the beginning. And then there's this kind of, it's called, right, like the initializable iterator, which is after a pass through, you could actually run a step. So for example, shuffling, and then run through that like iterator once again. So perfect, like use, or it's a perfect place to put in that shuffle step. So some of the problems that are being worked on with this dataset API is there's this concept that has popped up in some papers and some docs within TensorFlow about data, about specifically GPU data staging. And this all comes back to just trying to saturate these GPUs. And so there's this thinking that you can create a special staging area, and all, you know, you're just constantly processing and doing your pre-processing, and right, like essentially making the Q, what was it called back here in Q lands, the Q capacity, right? Yes, basically loading this thing up. And even, you know, way ahead of time. So just like really get this into like a state where that GPU can just wake up and continue to operate. Also, yeah, like there's obviously going to be more functional operators being added. You know, we saw this with Spark, where they started with the basic maps and filters and things, and then slowly added more. Also, something to keep in mind is, and this isn't so specific to the dataset API, this is more just kind of general TensorFlow processing. It's, yeah, right, like this area of like device placement. So device placement means, you know, if I have this graph and I'm doing a matrix multiply and then an add and then a summary of my current metrics that I'm like maintaining, for example. Some of these can benefit by being placed on a GPU. Some of these can just use a CPU. And these like device placement strategies at scale really, really make a huge difference, right? And there was a paper this week, and that was presented, and then also this was a paper from a couple months ago, actually. It was first presented, I think, at ICML in Sydney. And this is using, so this is Google Brain using reinforcement learning techniques. So explore, exploit type of stuff to figure out the best placement for operations. And this, what's cool about this is the device placement isn't fixed up front. It can actually change with network conditions and you know, various things that are happening, different batch. Yeah, if you think in terms of right, these like mini batches coming in, and certain characteristics of this batch might be best handled by this portion of the cluster, and you know, things like that. So think at scale, think all these workers that are like that right, like need to like communicate with each other. And okay, so I'm going to skip the feed queue thing because it's pretty straightforward, but we're actually loading data in from HDFS into TensorFlow, and then we're just dumping it out basically just to show that we have connectivity. Let me check the time. Oh, okay, we're up. Are people sticking around? We can go for about another 20 minutes and cover quite a bit. And also I'm recording all this, so. Train model CPU, train model GPU. Let's do these in a sec. Let me get through this. TensorFlow debugger. kind of cool. You just wrap your normal TensorFlow session in this debugger session, and you can actually, from the command line, you could do some cool stuff. So there's a notebook on that. Let me just keep going here. And I can leave the servers up till, like 2 o'clock, something like that. So this is single node multi-GPU training. So here's a case where we're speaking of device placement. So we're manually choosing which devices. This works for smaller examples, but at scale, right? Like again, you want to take advantage of TensorFlow's ability to like innovate on these like more advanced device placement strategies. So what's really interesting actually is if you do have a situation like this where you have one CPU with 2 GPUs, what will often happen, this comes up all the time on Stack Overflow, is if you don't manually set it and tell TensorFlow to use GPU 0 and GPU 1, like TensorFlow will like very often just choose a single GPU. And the thinking there is very similar to why you prefer a smaller Spark cluster, for example, or yes, how do I explain this? With Spark, for example, the more workers you have, the more communication, right, like has to happen. So there's a point when adding more workers doesn't really help and could actually slow things down. So by default, TensorFlow tends to feel that, especially for kind of toy examples, that a single GPU is plenty fast, and it doesn't actually need to do the distribution. So in this single node multi-GPU, this is a form of distributed TensorFlow. It's not across a network. So now, if you are using like the elastic GPUs, or if you're using Google Cloud and you have a CPU box with external GPUs, there sort of network communication going on between those CPUs and GPUs. You don't really, like, you're not supposed to think about it, but yeah, that is something to be aware of. But if you know that you have a single CPU with 2 physical GPUs on the same board, what's going to happen is a copy of the model gets sent to each GPU. So similar to how a copy of your PySpark code gets serialized and sent to each Spark worker, the same thing is happening with GPUs. And yeah, so if you think of your TensorFlow model similar to your PySpark code, yeah, that's a really good analogy there. And so each GPU has a copy of the model. Each GPU is pulling from some source for the data, and each GPU pulls a mini batch in, and they're different. And so one pass through all the data, each GPU sees 50% of the overall data set. And so this is why we do multiple passes through the data, right? Like multiple epochs through the data. And each time that we go through the data, what we want to do is shuffle, because we don't want that network to learn that ordering. We want each GPU to see different combinations of this data. And each GPU, like with its mini batch, it's doing a forward propagation on with the current values of the variables, right? So W and B. It's doing a forward propagation. It's getting that like prediction as though it was doing just a straight up prediction, and then it compares it to the actual label. And if it's off, it'll figure out how far off it was, and then it will backprop and start to assign blame, if you will, to all of the nodes and the layers that contributed to that prediction. Okay, so specifically, after each mini batch, each GPU has a suggestion, which is called gradients, for how much W and B should change. So at scale, this is thousands of variables, right? So each GPU then has to report to the CPU. The CPU is acting kind of like the, like PySpark, like driver program, right? And each GPU sends its hints or its gradients to the CPU. The CPU, knows about W and B because CPU is storing W and B. It then just will take an average. because the CPU doesn't prefer one GPU over a second GPU, or if there's 16 GPUs, it's just literally going to take all of those hints from all 16 GPUs and just do an average, and then update like those variables with that average, and then rebroadcast out the current state, that current value of each of these variables out to the GPU. So some of you might be thinking this might not be as scalable. This is synchronous, right? Especially in the case where you have 15 like GPUs, and especially in the more generalized case where you have a huge cluster, right? Like distributed cluster. Each worker has to send these hints across the network. And if there's a worker that's died, or a network that is super slow for some reason, this can halt like the entire training process. So we'll talk about doing it right. Yes, obviously we could switch to an async mode, and we'll talk about that at scale. Typically, it's being done async. One thing to note is when you say CPU :0, you are really saying use all CPUs. This is how TensorFlow will react to that specification. If you don't specify anything, TensorFlow will usually choose a GPU over CPU, right? But again, it will typically choose just a single GPU. With GPUs, you have to specify which specific device, 0 through 15. And if you use the Nvidia Docker to start up your Docker images, that actually mounts the GPUs, 0 through 15, whatever. There's another device that if you think of it logically like a device, it's called the XLA device. Now, we haven't talked about this. We will here in a bit. Very soon. That's the next section. But just know that you're saying use CPU, but also try to just-in-time compile. And so this is this XLA framework is the core to it opens up a whole ton of use cases and optimizations at both training and post-training. And so we'll cover both of those. But the XLA stuff, it's sort of an intermediate representation, and if you think of it best as the logical query plan that gets optimized and then gets converted into physical query plan. So that's what the XLA stuff says. So right now this is experimental, which is why you have to specifically say with XLA_CPU or XLA GPU. Our code has it in there. I think so there's 4 notebooks that we'll cover at the next break here. I'll just have you guys go through them. And actually, yeah, so that'll actually demonstrate. And what that's going to do is, where is it in the slides here? Actually, this is probably a good time. If you guys want to cover these 2 notebooks, and let's just take a quick 5-minute break. I just realized that this ends at 1 o'clock, not 12 o'clock. So yeah, so we have a little bit more time. What time is it now? I have to get some more water, basically. Okay, so let's convene at 12:25. And yeah, I'll answer these questions here too in a sec. Okay, so here's, actually, I'm just going to do the GPU example because it'll cover both. So let's run through this. If you're on a Mac and you don't know about this with Jupyter, this is one thing, this was worth the time that you're spending here, is learning about this line here. Make sure that you put Matplotlib into this retina mode, and all of your Matplotlib charts come out super crisp. Also reset, so this is, yes, I mentioned earlier that TensorFlow session can have multiple graphs, and you'll very quickly, like this will happen to you by accident, where you think you're operating in a single graph, but with Jupyter Notebooks, because they're a bit non-linear, the way that you can execute them, like you can do Shift Enter, at the very bottom and then go up to the top. Or you can like execute them halfway and something's taking a long time, so you go to on break and come back, and then forget where you are and then rerun it. What happens is you could get into a situation where you have multiple graphs that are duplicated, and there's really, really goofy errors that come out of TensorFlow that are not telling you this specifically. It's something like variable in use, or variable already used. What I do in that case is go up and hit this restart kernel, and I restart just to get back to a baseline, and then I just start at the top again. So this reset, and so the purpose for the reset default graph, you typically wouldn't use this when you're writing like a command line job or like a job that's going to be running that will die, because like naturally that session will disappear. But because inside of Jupyter these are long running sessions, this is a way to just clear out that default graph and kind of start from scratch. One best practice that I'm actually not following here, I should be, is you can actually create your own graph. So you would do like TF graph like this, and not even use the default graph, and then say graph equals graph. Don't worry about doing this now, but just know that this is possible, and then you completely eliminate the default graph, or this becomes the default graph, basically. If you don't specify anything, TensorFlow kindly creates you a default, but as we all know, defaults can lead to trouble, especially if you don't understand the extent to which their like natural life cycle. Okay, so here's, this is a time when we actually do want to create a config. Normally, we wouldn't really do this unless you're, doing some custom logging or, have some like particular configuration. But yeah, here's an example where we're taking advantage of the ability to configure when we create our session, and we're saying, you know what, use only 0.4 of my GPU. So actually, that's something that like we could change. We could actually just make it 1.0 or just 1 or whatever. So that's one parameter. This is if you're in like a multi-tenant type of environment. This is not very reliable. It is not something you should count on. If this is just kind of a temporary band-aid to get around the fact, if we did have multiple people that were sharing the exact same Jupyter environment, we would want to keep an eye on this, or maybe behind the scenes, we would not even allow a job to run that was going, more than 0.1, something like that. But just know that like you can do this. If you don't specify it, the default is it's going to use the entire GPU, and this actually is set to false by default. So this is the allow growth. So this is a bit backwards in the way you would think about it. If it's true, which we specifically do say, it asks TensorFlow to only use as much of the GPU as needed, and not just gobble the whole thing up when the session starts. Okay, so if this is false by default, it will gobble up the entire GPU. But anyway, just for like knowledge purposes, just know that these things are there. There's a few other ones that keep getting introduced. This is kind of that, like with Spark, when every new Spark release added about 500 more configuration parameters. This is the exact thing that's happening here. Okay, so we create that. We now have a session. Here I'm just going to use the fact that time continues going up, and I'm going to create a unique version that we'll use here in a bit. And I'm actually breaking my own rule, and I'm going to use feed_dict. So let me just kind of show you guys what's going on. I'm randomly generating data, like training data and test data, using NumPy random. I'm storing it in memory. I'm going to feed it in here soon. I'm creating test data. I'm plotting it. Here's my test data plotted, super crisp, retina. Now, this is interesting. So I'm specifically saying to store the variables on the CPU. And I touched on this a little bit, but whenever you have a scenario where you need lots of RAM, you typically go to a CPU or a cluster of CPUs. So because you don't want to bother the GPU with storing data, when it should only be used for storing its mini batches and for doing like GPU fun stuff. So CPUs, they're kind of boring. They have access to a lot of RAM, 4 terabytes in some cases. So we explicitly store the variable inside of CPU, which is why we actually have that. If we didn't put this here, if there was nothing, it would actually default to like specific GPU, like GPU 0. But because we want to control it, we have to actually say CPU. Now, this will get better. There's something called, well, I'll show it in distributed TensorFlow, but it's like TF, crap, what's it called? Replica, it's like replica device setter or something like that. So don't use this here because it's not even right, but something like that, where you would say, don't use the default, but use this particular method, which internally, this is where all of the innovation is starting to happen for like more, like complex strategies for like device placement. So we'll see it a bit here in the distributed TensorFlow, but for now, just know that for purposes of this particular workbook, we have to pin this to CPU. Here, we're explicitly saying GPU, even though we don't have to. This is doing the forward prop. And usually that means I ran it twice. Like whenever you see variable already exists, this means go up here, hit restart. It means I ran something twice. That's GPU. Okay, so we are still building up the graph. Again, this is not the this is lazy execution mode. This is the like most common. This like eager stuff didn't come out until TensorFlow 1.4, and it's still a bit. There's not a lot of examples of it. Okay, and then we're saying also on the GPU do this heavy lifting as well. So there's heavy lifting going on here because it's matrix multiply. And then there's a whole ton of, this is the whole core of, here's our loss function, which is just calculating the like average. It's, like doing root mean squared error. Or just mean squared error here. So it's calculating, it's doing the forward prop, then it's subtracting it from what the actual value is that we've passed in during training time. We square it, makes it positive. We then take the mean, and that is our loss. So this is the function that we're trying to minimize. And we're using gradient descent with a particular parameter called the learning rate. This is basically the step size, how far we're going to jump. This is actually a pretty high learning rate. Normally be something like that, but just found it to work okay with this data set. And then now we're saying minimize this loss. So like this is very similar to Spark, where if you read a Spark app top to bottom, you really don't understand what it's doing. Not unless you really know the internals of the operations. So here it built the loss, then we built the optimizer, and now we're combining the two into this like training operation. So let's run that. And again, we're pinning heavy lifting to that like GPU specifically. One thing about these neural networks, you do not want to initialize them to 0. The variables that we're trying to learn, right? So variable in TensorFlow speak is the weights, right? And so here we're trying to learn W and B. What you want to do is just randomly initialize them. So there's this convenient function called global variables initializer. You can actually pin variables to not participate in this, but if you do that, you're kind of at your own risk. Now, this is something, and so here's the actual values that W and B end up being. So this is the first time that the graph actually runs, right? So like this would be most similar to like a Spark action, right? Like something that's triggering the graph. And so these are the outputs. I could actually run this multiple times and get different values, but let's not get fancy there. Here's just the convenience method that's, again, triggering some action. And here, I'm just looking at my loss. So this is just a quick way for me to get the mean squared error. If we did no training at all and just stuck with these randomly initialized variables, let's see how high our loss is. And so loss is our error. So the higher the error, the worse off we are. We want this to be as close to 0 as possible. So if we do no training at all, we're at point, like 586. This is relatively far from 0. So this is exactly why we do training. All right, these next couple steps are just kind of getting TensorBoard logs ready to go. These are the event files, and these are the operators. This is an area I feel could be a lot simpler, and I believe Keras and like some other higher level APIs will be taking care of this more for us so that we don't have to think about these things. Here, when we start TensorBoard, which is already started, it's in the background, we point it at a parent directory. And then any directories that are created within, yes, any subdirectories, they will end up being a separate run, like a separate training run. And so here, like we're actually splitting this into training and testing. So we're going to train the model and then test it on a like a held out like data set that we fabricated up above. And graph is default graph. I don't know why we have to do that. It's kind of weird. So, and here's that version coming into play. So every run that we do will have this unique version. And then if we do 10 runs of this whole notebook, they'll all show up in TensorBoard. Okay, so that's just boilerplate stuff you need for TensorBoard. Close this here and zoom in a little bit. All right, now this is where all the magic's happening. So we're actually timing it. This is a nice Python magic here, right? Like IPython or like Jupyter magic that will output a timing for this entire step or this cell. And there's a lot of goofy stuff in here, but just know that we are going to trace. This is that boilerplate to give us the profile of where time is being spent in the GPU. And this is the file that's going to get output with that tracing info. And then I'll show you guys how to render it here in a sec. And session.run, this is the magic step that will start our job. So let's do it. Okay, so wall time 1.59, CPU time, time in user space, time in system space. And let's plot this. So we have a horrible fit, but that's okay. This is good for presentation purposes, good enough. So like, do me a favor, go back to your IP address and click on TensorBoard. All right, and you might have to click refresh a couple times. Actually, I'm going to zoom out because things get weird in this UI when it's too far in. So here's the loss. So this is the scalar that we were tracking. And there are actually 2 lines on here. It's kind of hard to see. You can do just one at a time. You can do both. So these are very similar, but they're actually different. So because our data set is so small, the values that, yeah, these sort of track along the same, the test and the train. So that's interesting, and that's cool to see. If you, and then if you do zoom in and stuff like that, if you double tap on the graph, that took me like about 1.5 years to understand or to find. You can get back to the full version. This is where you would see if things are not converging, if you're plateauing, if you're actually going up, specifically for your test. So your training might converge and go down to 0, but your test, the sort of generalization, yeah, that's the way to like quantify how well like this model can do on data that it has not seen. That could potentially plateau or even start going up, and then that's an area of concern where you would want to stop the training. Now, this is the cool thing here. So click on graphs, and here's your runs. So you should, if you don't see these, just click refresh, or just click in the browser. I think it refreshes on its own every 30 seconds by default. Pick one. You can either do test or training, and click on the device down here. And now you see this legend that shows up with blue and then green. And green is the heavy lifting, that's the GPU. And blue is the boring stuff, which, zoom out here, would be like storing the bias and storing the weights. Okay. Now, you'll actually, some of you might notice, if I can get this back to here, that this gradient descent appears to be blue. And why is it being done on the CPU and not the GPU? Well, actually, let me zoom in here. This is mixed. The actual update, which is a very simple operation, is being done on the CPU. The gradient comes in from over here. So the like dominating like operation here is just a simple add and then like average, but you could see the green coming from over here when you click on that. It highlights over there. So these little boxes, if you want, like you could actually do these yourself. So I could have put the entire forward prop into its own like namespace. So these are called namespaces, and just kind of best practice, if when your graphs do get more and more complex, you want to start namespacing things so that you could treat them as one combined thing and not have 8 billion nodes around there. Okay, so that's that. Go back to here. Here we're going to save the model. Now this is using the old style, the classic, the train saver. This is the old way to save, and we have to do that because some of the post-training optimizations can't work with the saved model format. They just haven't kept up, or the developer that built these post-training optimizations, doesn't have time to support both. So here we're actually writing out the graph, and then writing out the actual checkpoint. So again, this is graph and then variables. So here we've created the .pb is protobuf. We're calling this unoptimized because I'll show you here in a sec why it's unoptimized. So let's list everything. There's our metagraph. Our .pb is protobuf. That's the a like binary representation of our graph with the edges and the nodes. Some index files, things like that. So this is kind of a fun little tool. It's called Summarize Graph. This is, I don't believe this comes with the pip install. It actually might now, similar to the save model CLI. But here, this is just giving you kind of a, this is running a bash command. And you point it to your graph, and it can physically tell you what's in that graph. So this is interesting. There's 19 nodes assigned to CPU, 63 assigned to the GPU. It kind of, gives you like an ability to run some benchmarks. if there's one other piece of code that you want to snag, it's this. This is very likely the first time this like bit of code is the first time that you've seen anyone render a graph of a TensorFlow graph inside of Jupyter Notebook. And so these 4 lines here do it, these 4 cells. So this is what I was saying earlier. This is linear regression after it's been trained. And there's a whole ton of things in here. You'll see broadcast gradients, apply the gradients, boom, boom, boom. All these, like, yeah, there's a bunch of identity checks and yeah, there's a whole ton of stuff. When we go to serve, all we want is, you know, this is our matrix multiply, there's our add, and that's it. Actually, it would be over here. Boom, 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 boom. Okay. So that's unoptimized. We will optimize here in a sec. I'm going to skip the debug. Distributed, we'll probably skip that. I'll just talk through it. And then I do want to get to XLA. Oh, and then one thing that's really cool I didn't show. So during training, we generated this timeline-GPU. There's a Chrome plugin. Yeah, I know this is super wonky, which is why it's being rolled into TensorBoard in newer versions. Oh, so first I have to go back to my notebook. You can install this plugin, it's the Chrome tracing plugin, but it works on a local file. Do anything? Try it again here. This is going to show, yeah, so there we go. So this is that same view that I was showing before where memcopy is happening, what the streams are doing, what all of the streams combined are doing, CPU. You can drill into these things. So here, you know, you can see the tensors at play, the operation name. So we will generate this here in a sec when we optimize, and we'll see some pretty big differences. Okay, so let me jump back and get as much through the slides as possible. Okay, distributed TensorFlow. So sort of a generalization of this concept of distributed, you know, this is one node, but multiple GPUs, ideally on the same motherboard. This is, we have given up. There's no server that currently lives that can handle the size of our data, our mini batches, like we want bigger. We have, you know, so here we have 3 workers. So these are on the right, and each worker has 4 GPUs. And then there's this common like CPU parameter server. So, or this actually should be called parameter cluster, right? When people say parameter server, it's really like typically implemented as a like cluster, and the parameters are sharded, or the weights, or right, like variables are sharded, where, you know, each a section of the parameters is being stored on a specific node, like within that cluster. So there's, yes, obviously that's the stateful part of our whole training process. The stateless part is these GPUs. So each GPU gets handed its own copy of the graph in right, like the most typical case. And each GPU then pulls from a data source. And so one pass through the data, there's 12 GPUs. One pass through the data, each GPU sees 1/12 of the entire data set, which is why we do multiple, right, like passes, right, yes, multiple epochs through, right, like this data set, and we shuffle, yes, in between. And so each GPU after each mini batch has its like gradients, its hints as to which way each variable should go. And instead of, so there's one cool optimization that TensorFlow does, and actually Spark does this as well too. It can pre-aggregate on each node, and instead of making 12 separate calls from each GPU into the parameter server, it will actually pre-average on each worker and send one update per worker. So that just reduces communication to the parameter server. The downside is that you're pre-averaging and then doing another average based on the number of workers, but at like this kind of scale, like communication, so lowering communication certainly helps. And then I guess on the left here, I kind of started on the right. The left is, so the purpose of this is to show on a single node with 2 GPUs, this is pretty easy. On multiple nodes with a single GPU on each. So TensorFlow will, right, like by default, so there's no changes on your end as the developer. But on like TensorFlow's side, it will recognize that it's on separate workers and it requires communication through a network, and it will physically put in the send and these receive nodes where that like cross-worker communication is happening. And like, yeah, so like behind the scenes, it's using gRPC, it's using like protobuf to do this communication. This is the area where like Yahoo came in and contributed like an RDMA like version. So also this hints at something that we really haven't talked about much, which is splitting the graph over multiple nodes. So when I was talking about like this previous example here, we copied that model into each one, similar to how we would copy like an entire PySpark function and send it to each worker. That's much easier in terms of like communication pattern and kind of reasoning through like performance issues than when you're splitting the graph itself. And so the reason that you would split a graph is if the operations, right? So it's not the graph itself. That's a really small file because it's just edges and nodes and things like that. It's stored in protobuf, which is right, like pretty optimized. But the problem is if a portion of the graph, right, like requires for its execution for B and C to happen, right? Like let's say this is some kind of matrix multiply. We need a certain amount of RAM that's larger than the current 16 gig limit on these P100s and these V100s. So at that point, you have to split the graph across. And part of it, so A, B, and C is just too big. And so that has to be split across. And so this is called model parallelism versus data parallelism. And the short of this here is that you like typically want to be data parallel, and this is kind of a goofy name. There's this other term, between graph replication. So I think of so like model parallel, for example, this like totally brings up all these like distributed graph types of problems. So if you've ever done any like Spark GraphX or anything like that, or tried to like distribute like Neo4j or TitanDB, like thinking through some of these large graph problems. And what you really need to know is, if I back up a slide, the communication pattern. So this particular like developer chose to split and put B and C onto this worker and A onto this worker. And they did that because they felt that this is the minimum amount of communication for this graph that can satisfy the RAM needs of my of this training job. Okay, so said differently, all of the parallelism that we're familiar with from Spark and from Hadoop is called data parallel, and that's the sort of easy one because it's the exact same model, or like it's like the exact same code that's running on each node, and it's just operating on a different partition of the data, right? Like with the assumption that they will be all reduced at some point back into one final answer. So with model parallel, each partition of the model has to see all of the data, whereas data parallel has the same model and sees partitions of the data. Okay, here's synchronous versus asynchronous. This is that thing I was saying. If I back up a couple slides, this is all fine and dandy because it's on the same motherboard typically, where you have multiple GPUs that, this pipe will, yeah. So like the pipe between CPU and the GPUs, which is typically PCI Express, is like fairly stable. And while one GPU might actually slow down depending on the types of batches, if it's just getting unlucky batches that are really, really, like compute. So if like CPU 0 gets like all blank images and then GPU 1 gets, more complex images, let's say, GPU 1 could start to lag behind. And that would slow down the whole training process, even on a single node. So pretty much by default these days, even like the estimator API itself by default chooses async. And this is basically, this is required because at like larger scale, when there's tens of, thousands of nodes, there's a high probability that some of these nodes might actually crash. And it's very likely that there could be like network communication problems going on. And it's even more likely that they could get out of balance in terms of how fast they can keep up with their batches, okay? So like this async does not require all of those workers to report for those new values to be, those gradients to be like averaged together and then those new values applied to like those weights and then those weights to get rebroadcast out. So like said differently, if you use async mode, you can survive these sort of slowdowns, right? Like latency, so that's actually more scary than failures, right? Failures, you at least know right away. You could do health checks and spin up a new one. If you have latent, right, like workers, that's actually the worst case scenario where they could be coming up just enough to satisfy the health check, that like heartbeat, but they are effectively slowing down the entire training. So the short of it is, if you use async, it works much better at scale. Synchronous is a bit easier to reason through, and with the async mode as well too, you could be dealing with stale gradients, which could potentially slow down convergence or actually like prevent convergence. So something to keep in mind. I'm going to skip over some of these things. I just think we are just going to run out of time, but these are all the failure cases. And also you want to be using this estimator API. There's also the experiment API, which is even higher level than the estimator API and kind of ties everything together. So let's start like with the estimator API itself. Supports Keras. It's sort of a unified API for running your job locally and on a TensorFlow distributed cluster. The sort of early versions of like TensorFlow code, and actually the most common versions of like TensorFlow code are sort of top down, right? They can't, it's not very easy to like split them up for like distribution. So this is a remnant of the fact that distributed TensorFlow came out about 3 months after core TensorFlow. And so all of these demos and all these examples and, 40,000 stars within a couple days, that stuff, right, like created a lot of bad examples. And so this estimator API is an attempt to kind of right that ship a little bit and give you a single API that can, right, like very easily run locally and on a cluster. And so something that, so this is one of those areas that like you can tell came out from the Cloud ML Engine product management team, right? And specifically the experiment API. If you go into Cloud ML Engine, that whole interface is based on this concept, right, like of the experiments. And so each run is, so that shows up as a line item in your dashboard showing, right, like the experiment name, like the data set used for testing, training, and validation, blah, blah, blah. So the problem is there's very, very few examples of this. You can also do hyperparameter tuning also with these experiments. You can give it a range of like learning rates. range of batch sizes to try, and you can tell it how many like nodes to use in parallel, right? Like basically cap the amount of money that you're willing to spend, and figure out and if you want this to complete quicker or to be like a little bit cheaper. Yeah, also like this estimator API really sort of opens up this kind of downstream, sort of optimizing and serving infrastructure, which is like the exact space that like Pipeline's in. So what we struggled with even as recent as just a couple months ago, like we've now switched everyone over to the estimator API, or like said differently, all new projects that we're getting involved in have the estimator API. But like previously, we had to do all these weird things where we were splitting people's code up so that it could run in a distributed manner. And like that's essentially what the estimator API does. So instead of that code sort of executing top to bottom, there's callbacks now. So when it gets to a point where you're like executing this graph and it needs data, it just calls out to like what's it called? I think it's like input function. And that like input function can work across multiple nodes. And yeah, let's see. Yeah, so there's callbacks and there's hooks for things like writing summaries and all the normal stuff. So it's kind of this non-linear sort of callback, sort of functional type of architecture. So more on the estimator API, trained to serve. There's these canned estimators. I'm not gonna spend too much time here, but one thing to know, there's, so for the experiment API, this is where you can start to introduce hyperparameter tuning, and just think of this directly as a like line item inside of some dashboard that's showing for a particular set of like hyperparameters, what is like the actual training, like accuracy, and let's see what else. Yeah, so like the estimator API defaults to data parallel and to async, so that's good. It's the like easier parallel. It's not model parallel, and supports this kind of like notion of failure recovery for our workers with the async. There's a note here that you can't. It's not possible to like auto scale. So once these training clusters start, you have to tell it what are all the nodes that are participating. And because we're using async, we can afford to lose nodes, because like they'll just get spun up and then start to participate again. But you can't add new nodes that the job does not know about. But I don't feel too bad about that, because really you're not auto scaling that much during training. Right? Like normally you've got some fixed budget. You have a fixed set of CPUs, a fixed set of GPUs, and like you're not really auto scaling up and down during training. So yeah, there's just some more details on how to get this working. There's some gotchas in here that I struggled with getting this to work. One note is that the pipeline CLI, if you install it, if you follow off the main pipeline site, off of like the main GitHub, there's ways, there's a cluster section where you can use the pipeline CLI to actually do a like distributed training job, and it will generate all the configuration. And right now we support Kubernetes. We're getting distributed training to work with SageMaker and the Google Cloud Engine as well too, which is pretty easy. Yeah, like once you get it working on Kubernetes, then things tend to fall into place elsewhere. Keras, here's these canned estimators. So the little metric up on the right said sort of differently is 58% of Google internal projects are like using these these canned estimators. And so these are like commonly used estimators. These are pre-tested, pre-tuned. They're used by a whole lot of people, internal and external. They're a really good place to start. You should always use these if possible. There's things like TensorFlow Estimator, Deep Neural Network Classifier. There's also this feature column sort of API here that kind of came out of nowhere. It's part of the Estimator API, and it will let you like represent and do like one-hot encoding and do like feature crossing and things like that, where you can generate new features like based on combinations of features. So here's an example of the like input function right there. So this is a separate function, and when you create your estimator, you actually pass it that like input function. And so here we're, so this is using the estimator API with the dataset API. We have a generator, which could be pulling from HDFS or could be randomly generating, whatever. There's like the like iterator, and then we're starting to like do the actual iteration and then return that tuple. And as long as we do that, and this can handle distribution, then we're in good shape, which that dataset API does. Here's something specific to like TPUs. So this is what I was saying earlier, is we're starting to see TPU-specific stuff that's creeping up inside of TensorFlow. So I assume at some point this will make it more into the core like mainstream. Right now, this is, I believe, part of Contrib. But there's some slightly different things. So instead of creating just a base estimator, you have to create a TPU estimator. And this is specific, hardware that like Google has created that is not general purpose like the Nvidia GPUs, but is very specific to these kind of like workloads. So there's also, instead of doing gradient descent optimizer like we did before, you actually have to wrap it in this TPU optimizer, cross shard something something optimizer. And you then have the same code where you're like minimizing the loss. And so just know that there's starting to become TPU specific things in there in anticipation of a public release of TPUs, which I'm sure will happen right like sometime next year. This is something to keep in mind too, and like the estimator API supports this, TensorFlow serving supports this also. It's the ability to output two predictions or two like fetches, if you will, right? Or two like outputs for a single pass of my inputs through the graph, and so through this network. So think of the ability to pass in one set of features or like a bunch of rows of my features, and out comes both a prediction, right? Like for each image, I predict this is a church. I predict row 2 is a penguin. 3 is like something else. So that comes out, but then secondly, from my prediction, I can get that very last activation layer. Okay, and now so that's a like numerical representation of my input, which can then be passed into a subsequent model as the like numerical input, and then scored again. And so this is where we start to see ensembles that are creeping up. More and more people are starting to compose. This is one area where like Keros's functional API really comes into play. So right, like Keras has both a sequential kind of top down, and then more of a functional API, and which right, like this like really opens up the door for like model composition. So you can like get multiple models from different teams or like different people that are working on a sub problem for this prediction, and chain these things together. So it's not one big model. And so what's cool is, think of the most common case, or what should pop into your mind is you have three different models, and you want to get the prediction from all three and then sort of average, right? Or like somehow that's actually a like slightly different type of example, but you want to like basically get the prediction, but then also chain so what you're doing is using this neural network as a feature engineering step, right? So it's giving you both a prediction, but then also taking this input, transforming it into, it's taking this like human readable image, this like human viewable image, and then converting it into this numeric representation and a prediction. And now, so we store the prediction, we then run it through the next model, and maybe, so like that model has a prediction. And then we take the outputs and then pass into a third model. And now And so what you do is then either average all 3 predictions, or if you have a majority where 2 are saying it's a penguin, then 2 of 3, then you send back penguin. Okay. So that's a long way of saying that there's multiple heads or multiple objectives is really the best way to put it. Where you want a prediction, but then also a like numerical feature engineered representation of the input. This is supported by TensorFlow serving. And let's see, layers API. This is actually, yeah, I'm just going to skip over that. Feature column, I'm going to skip. This is just typical categorical, ways to represent features, one hot encoding, bucketizing. These are just the terms used within. So, right, like again, this is all, feature engineering, yeah, the embedding columns. Feature crossing, I didn't get a chance to actually fill out this slide, but this is where you would do multiple combinations. You could actually dynamically fabricate new features. So this is one of those exploratory things when sort of early stages, you would drop down to floating point 16 and just figure out which features make sense, which features, like get you close, and then you would drop back to floating point 32. Separate training and evaluation. This is one pattern I've seen over and over in just probably the last couple months, and this is because of the estimator API. This is a way to isolate and keep training going, and then in parallel, every hour or so, let's say you create a checkpoint and tell the parameter server or that cluster to save all of its variables. And then every hour, the evaluation cluster spins up and grabs that latest checkpoint from HDFS or from S3 or something. And so now there's this evaluation cluster, which can be much smaller than the training cluster because it's only operating on 10%, 20% of the data. And what you're doing here is you're keeping training on its path and not burdening. You're sort of optimistically continuing to train, and you would only halt that training if the evaluation cluster, which is running in parallel, finds something worth stopping, like loss function starts to rise or flatten out, which means you're starting to overfit. I'm going to skip the distribution. We need to cover this section, then probably have to do the serving stuff some other time. XLA, yes, this is that layer I was talking about. So there's a lot of hardware that's starting to pay attention, so there's a lot of chip manufacturers that are paying attention to this XLA framework. So at NIPS this week, for example, there were a bunch of Qualcomm people there. There's a couple startups I was talking to, hardware startups that are watching this particular project super closely. This is used for a couple different things. On the training side, this helps do the just-in-time compiling. So this is that logical to physical sort of layer. It's that in between. And let's see. So this is obviously where TPUs come in. So Google, they've been implementing XLA, physical operators specific for the TPU, and then same with these hardware startups as well. So here's another view of it. It's sort of, there's this high-level optimizer syntax, and that's kind of the logical, and then it gets optimized, analyzed, constant folding, all the normal types of things that we think about even on the data processing side and database side, independent of source and target. Yeah, so the output is more of this HLO stuff. So it's kind of the logical plan, then an optimized logical plan, and then it gets converted into physical plan. And right now, this XLA stuff actually relies on LLVM to go that last mile to the native, that x86, ARM64, and there's even NVPTX support, so GPU support. This is the layer where hardware manufacturers will step in and take that XLA that second like yellow box there and build their own specific for their hardware. So just-in-time compiling, yeah, this is very similar to Spark's, what's it called, Project Tungsten. And like specifically Project Tungsten 2.0 and Spark 2.0, where Spark actually, during its data processing, can figure out which operators are being used commonly together and can physically fuse them into one Java method, to one Java function, which from a like JVM standpoint gives you huge performance gains because you're now, right, like there's just way like less virtual table lookups and yes, things like memory movements, right, like moving data. If you have to call 15 functions, that's way slower than calling one big function that's doing 15 things, just from a systems standpoint. So this is where loops get unrolled and see fusing. There's some layer fusing too that can happen. That top example, so yeah, this is where you would say with device and then give it like the XLA version. And then this is a debugger here where you could dump out the HLO. Okay, so here's a like visualization of what happens here. So I showed that picture before of these 15 or 20 operators that are all, so this is like before optimization, right? Like before JIT compiling. After JIT compiling, that same single GPU 0 gets one big function, one big kernel has been dynamically built, similar to how Spark can like dynamically build one Java function. And so again, we can profile it using this like boilerplate code, and yeah, after JIT compiling, you could see, and this isn't to scale, but it would end up being like less time. Here's kind of a like visualization. This is what those hardware companies are spending time looking at. This is so what you're seeing here is that, so like this is one big difference between Spark and TensorFlow. When Spark came out, and still they have this view that they are powerful. Spark is powerful because it's so like general. It can work on general purpose hardware. And yeah, this was always something I felt was kind of weird because there was a lot of like GPU talk and people hacking Spark's code base to use like deep learning for J. And yes, IBM was, as part of the Spark Tech Center, there were about 5 groups that were working on GPUs plus Spark. And all of them approached Databricks with these suggestions and different ways to tune. And like Databricks, like essentially shut the door and said, no, we are only CPU. This is the most generic. You might see a GPU specific version of Spark that comes out of Databricks proprietary like product, but I figured that probably would have been here by now, but it hasn't shown up yet. But for sure, the open source project does not support GPUs. And this is a different strategy than what TensorFlow, they, from the very beginning, like you could tell with these types of like visualizations, they want people to build right, like target specific or like device specific, right, like plugins for TensorFlow. So, and as you can imagine, right, like once you sort of get into the hardware, and these hardware manufacturers start to build towards your tool, yeah, so that's where things tend to stick, right? And that's where the true scale comes from, is small device, things like TensorFlow Lite, right, like I was talking about earlier. Okay, so that notebook is pretty much the same thing, but it generates an XLA version. Same with that. Let me cover, okay, so from this point on, it's post-training. And so we're going to optimize and serve models after they've been trained. So this is something called AOT compiling. So this is the ahead of time, before it was just in time. Yeah, so now we've got our trained model. So we have a graph and we have weights. And let's see what we can do with these things with the XLA. So this like AOT compiler, this is actually very similar. This still exists. It's a bit wonky to get working. TensorFlow Lite is basically the same thing. But it's geared more toward like mobile devices and like tiny sensors, and so it has a different set of operators and things like that. This is a way to tell TensorFlow that, so here's my graph, here's my inputs, here's my outputs, and give me the smallest binary possible. So like give me that like .h file and that .so, right, like linked or file that I can link into my app. And so this is where, you know, some of these people, what's my buddy working on, like this cart that, so it's this autonomous thing that, you know, rolls around. I think they're on the Berkeley campus, and it's like delivering food. And so this is using TensorFlow. So they actually use this to get the size of the binary down so small that it can actually get updates, you know, through a pretty small bandwidth, right, like Bluetooth device, something like that, right? And it's not this huge, you know, bloated runtime. So I had described this earlier, but like one thing to note is that there's no GPU support for this, which is very interesting. So you know, can like bet like pretty much anything that there is TPU support, and it will be very easy to go to take your graph and simplify it down to work on these TPUs. There's really not much advantage right now for, you know, Google to spend time building that GPU version, but you know, so if like the Nvidia folks show up with it, like that'd be great. Also, we can just directly transform our tool. So this is really cool. This is called the Graph Transform tool. This sort of came out from the community, but was built by this guy, Pete Warden, within Google, who focuses on like mobile devices, things like that. And this is a way to physically, right, like iterate through your graph and strip out nodes, or do weight quantization. So, you know, like take your weights and drop them from 32-bit down to 8-bit. Let's see, you would do, you know, constant folding. You could do your final batch norm folding. So those like, yeah, so that final mean and final variance per layer can be burned right into, so one matrix multiply upfront at this stage will right, like make adjustments to all of those weights, right, yes, at that layer. And that's done once. If you like don't do that up front, what happens is each prediction that comes in has to adjust for that final mean, final variance. So, I mean, it makes a lot of sense to perform that calculation once because of the properties of like linear algebra. This like makes sense, and not take the hit per prediction. Yeah, speed up math. You can actually make compression. So if you round weights, this actually won't change the size of your model too much, but in terms of compression, will give you a pretty good like compression ratio. Okay, so here's where this ends up. This is before optimization. That model becomes that, which we already saw, and then we can run this graph transform thing. So now some of these things are actually done for you now when you do that saved model export, that special saved model file format, but not everything. So yeah, let's go through. So this is one command that actually does all 7 of these things, but I'll show kind of step by step. So so this is that very first one, strip unused. And like notice that I'm giving it the unoptimized, I'm giving it, which we had just trained, I'm giving it the output, which is called optimized. And I'm giving it the input, which in our graph is called x_observed. And then output is that like operation for our fetch. And so that's giving it the start, the finish, and then all the operators, all these transforms that we want to happen. So with just one transform, we go from that big like gobbledygook down to just this. And like you'll notice that, so these right now are placeholders. Yeah, this term placeholder, yeah, I should probably mention, is a, it's kind of a, well, it's a placeholder for when, for right, like something that has to come in from outside of this graph, right? So things that would come in outside the graph, At training time, you're getting both X and Y for the linear regression. At serving time, you're just getting X. So, so here, because this is all set up for training, all of these things are placeholders. Now we'll see as we go through and freeze the graph and do some other stuff, this will end up being that simple, what we see back here. Yeah. So here, so yeah, after one pass through, there's these pesky identity nodes. Let's see, those things don't need to be there for serving, so we like literally strip them out with this remove nodes. We do some constant folding. Here, we're actually not using batch normalization for this particular graph, so it doesn't really do much. Weight quantization, the graph stays the same, but the actual file size, you know, because we're going each variable that we were representing, you know, which is only 2 variables here, it like was 32-bit, and now each variable is just 8-bit. So we've like lost a little bit, but we've made this file smaller. It's not that much smaller because it's only 2 variables, but with lots of variables, this would come into play. So weight quantization, just like real quick, this is if you plot your so you've trained your model. There's a bunch of weights, and if you like plot all those weights and then shrink it in to so before floating point 32, the value of like these variables can pretty much be unbounded, right? Like relatively. I mean, this is a huge space, 10 to the 38, right? Like negative to positive 10 to the 38. And what we're doing is shrinking. So like floating point 16 will like linearly shrink them into negative 65,000 to positive 65,000. If we get even crazier, we can go to int 8, and each value of our variable now has to fit in between negative 128 and positive 127. And so it's still the same distribution, but we're just simplifying. All right, so there's also this idea of activation quantization, which is pretty crazy. It's the one thing to note. So what I was just describing was this W layer right here. So W0, 1, 2 to M. That's the weight quantization. So let's say that we've done that. Now, what we want to do is narrow or like simplify the like output from our like sigmoid function. So this is actually the first time that you see like an actual neural network, the classic like display of it here. But you have these inputs, which are X, which are placeholders, times our weights, and then these get added. And then this all so these get combined, and then that value gets passed through the sigmoid function, right, the activation function. Then we want to quantize. So effectively what we're doing is we're simplifying or like reducing the space that is being represented by both our weights and our activations. And once we can like, and so once we can shrink down that space, so this is a huge, huge difference in both the processing times for these like matrix multiplies, right? Because if you multiply 2 int 8s, that's way faster than 2 floating point 32s. So on the forward propagation, on the like serving side, our calculations become much faster. But at the same time, we can now shrink the size of our variable file, right? That file holding all those weights can go down like it like goes down pretty significantly. From, for example, 90 meg, I think is the inception model. Just doing weight quantization gets you down to 20 meg. And then you could further do this activation quantization to get even more and fit on like really small devices, right? Like these, like security cameras, things like that. One thing to note about this activation quantization is it depends on X. And so you might have already like realized this, that so before, for the weight quantization, we knew all the weights up front. So if I back up a couple slides, we knew this whole like distribution. If we go here, we don't know the values of like this activation because we don't have any X, right? like there's no data that's been passed through. So this is how we get around it. We actually calibrate. That's the official term, and you run through samples of X, and this is sort of hand wavy. It's a representative data set. So like you want a good data set across all the different types of the inputs that could be coming in, and what happens is you turn TensorFlow into a learning mode. So this is a slight asterisk on me saying all the optimizations are post-training, because we're actually not technically retraining this network, but we're just calibrating this sort of step for the purpose of like simplifying the output of our activations here. Okay, so said differently, we're just getting the model file down to a small file. We're simplifying our calculations. Oh my God, it's like a huge motorcycle thing going on out here. And the way to do this is with a one simple pass through. So really, this is like 1,000 images maybe, and this can be done on very, very small hardware in pretty much no time. That TensorRT project that I had mentioned earlier actually has this built in as part of it. And so you just point it to a directory, like a calibration directory. It then can read that in, and I'll show you here actually. This is the output. So yeah, so earlier, all of our things up till now we're simplifying our graph. So I'm just backing up slides here. We started with this big gobbledygook. Going forward again, we were doing more and more of these post-training things to get our model to be smaller. Now we're calibrating. So for the activation quantization, this step actually creates a more complex graph. And so this is a hint that we likely need for something else to happen, right? And so you see min and max. This is where it's capturing as that calibration data comes in. It's capturing min and max, quantizing, doing a bunch of stuff, figuring out the ranges, and then dequantizing, boom. And so, but we still need to get it back to that simple version, right? We still need to get it back to this. So going forward again, there's this extra step called freeze requantization ranges. So this puts this model back into a learning mode. It's pretty simple learning. It's just taking that data and doing min and max and doing some stuff here, a couple matrix multiplies. Yes, after that's done, you then would freeze and recreate, get back to this. Okay, so pretty crazy stuff. Not a lot of people know about that side of things. Definitely these are things that you will want to test with, even on your server-side models. So things that are not destined for a mobile device. You still want to do a lot of these things. And so the ability for a data scientist to actually play with this kind of stuff, right? So this is after this model's been trained, before it gets handed over the wall. Let's try a couple different variations here. Yeah, so even locally, right, with the way I was showing with Pipeline earlier, where you can run the model locally, you could actually do this and test it locally and, compare the quantized version with the non-quantized version. And yeah, maybe it could be slightly faster. It will likely come in about the same on your laptop. If you're using GPUs, might come in a little bit faster, things like that. But it will all depend on type of environment that you have. Okay, so TensorFlow serving. This is the last section. Go through here. Here's that multi-headed stuff coming up again. Here's that signature def. Yeah, there's multi-headed. One cool thing is that you can actually embed TensorFlow serving in your code. So there's another .so file. And this comes in handy when you have, you want to use all of the innovation going into TensorFlow serving, but you don't want to run it as a separate process. Maybe it needs to be in an embedded type of device, and maybe you want to build a, like circuit breaker framework, which is something we use Istio for actually, on top of like Kubernetes, with TensorFlow serving. If you want to do things like batch inference, for example, versus the typical request response, if you want to like do things asynchronously, right, like that kind of stuff, you can actually link in to your own. There's no real clean way to do this with Java. It's C++ type stuff, and there's no chance with Python. So I already talked about that. And yeah, here in this notebook, we just create and deploy the optimized. I don't think we're gonna have time for this. I do want to show this slide. So one parameter that you can play with at serving time is this idea of a like request batch size. Okay, so the ability to and this is a feature of TensorFlow serving, but this is certainly something at like the Istio level, for example. This is something that like we do where even at a higher level, so non-TensorFlow specific, even for like scikit or just a JVM model, PMML, right, like something like that, we would actually batch up a whole bunch of requests over 20 milliseconds. And because at the end of the day, we're just like basically doing matrix multipliers, right? Especially with the forward propagation. So if we can, instead of making two separate calls, so here's like request 1 comes in, that's in green, and then there's like request 2 comes in, and that's blue. If 1 and 2 can get batched up together into one big matrix multiply, this is huge, right? This is huge performance gains. So this benefits us. Right, like because of the properties of linear algebra, right? Like we can actually do one big matrix multiply, and then on the way back, because we controlled those offsets and put them edge to edge, what we're able to do is figure out, so that result, the top 2 go to customer 1, those bottom 2 go to customer 2. And so that's really cool. So these are 2 separate users that are potentially on like opposite sides of the world that happen to end up on the same TensorFlow serving process running on a server somewhere. They can both get batched up, one big matrix multiply. On GPUs, this is huge, right? This is very similar to how we were fusing together, right, like multiple operations, except here we're actually fusing together multiple requests. And then doing a single operation. So if you can move once and do one big calculation, right, that's much faster than doing multiple moves from CPU to GPU. Yeah, some advanced. Yeah, there's classically with TensorFlow serving been some problems with recurrent neural nets. So there's some, in terms of performance, there's been a little bit of innovation going on there, and I think that's it. Yeah. All right, how far over did we go? Any questions? Please post them. Give me a sec here to look. Oh yeah, we're only 45 minutes over. Okay, that's easy. Thanks for sticking around. Please post your questions. Let me pull up the notebooks real quick and cover anything that stands out. Distributed TensorFlow. Yeah, this is kind of cool. Actually, 5A is the more interesting one here with the GPU. So we actually start up 2 servers listening on different ports. We're doing a compute-heavy matrix multiply. Actually, we're raising this matrix to a power. Here we're assigning to the CPU. So we're raising A to a power, we're raising B to a power, and then we're summing A and B. And let's see, we do one on CPU, one across CPU and GPU, and then one on both GPU and GPU. And as we would guess, the GPU is faster. One thing I do want to point out, the first time that TensorFlow sees a GPU kernel. So, so physically, so the code for that kernel gets compiled and stored inside of the GPU itself. So if we had run this like just totally cold turkey, actually, if I run this again, it should be faster. That was 1.2 seconds, 0.91. So this was the first time that I had run this particular kernel, which is, you know, doing matrix probably multiply a bunch of times, like recursively. And the first time I ran it, this was 1.2 seconds. The second time I ran it, it's coming in at, you know, like around, oh, yeah, actually, that's the CPU, sorry. 0.77. Right, like the short of it is, the first time each GPU, so if you have 16 GPUs and you only hit the first 8 GPUs for your first training, and then you start up a second job, right, like right after, and point it to the next set of CPUs. I don't know why you would do this, but right, like just know that the first time the physical chip sees new code, it's going to compile it, it's going to, you know, convert it into NVPTX, and then store it in like, right, like the actual cache, right, like the instruction cache. And that takes time. So the short of it here is on Stack Overflow quite a bit, I see people doing performance benchmarks and they see very wildly different, right, like performance the first time running through than, right, like subsequent times. And this is physically just a limitation of the GPU. And they see it too when they like run a job, they only use one GPU, then they rerun it and use, you know, the other 15 GPUs. And they're trying to figure out why is performance weird. Like, yes, basically each new GPU that sees this new code, yeah, has to take that hit. Here's the XLA stuff. There's really nothing different about the code except you have to point it to XLA. Everything else is the same. Oh, and then also it would generate those visualizations that I was showing before. So let me do the GPU one here. So I created the same thing, the unoptimized, except it's called XLA GPU. Let's see, we should see these files pop up. So here's the XLA stuff, the JIT stuff happening right before our very eyes. So this is step 1, this is step 75 here. And there's like an entire page off of the Tensor. Oh, and if we pull up, we should be able to compare now. So here's that timeline XLA. We download that. Go back to our Chrome tracing. XLA GPU. We should see the XLA stuff kick in here. And copy, where did it go? It's in here somewhere. I think it's like super tiny, but it'll say XLA launch. Oh yeah, yes, here it is right here. So if we do these side by side, so here's 0, 1. So yeah, here's a bunch of, you know, these are different swim, right, like swim lanes going through. Oh wait, is this the CPU? Here's the GPU. So there's a bunch of operations happening at the beginning, and then these things get folded into one single XLA versus separate ones there. That's kind of cool. Yeah, this is the graph transform. This is basically produces those screenshots that I had in the slides, because we typically get cramped on time at the end here. And deploying. So like again, here's that freeze graph step. So because we manually post-processed, we have to refreeze it. And this is a bit of TensorFlow magic. This is like hours and hours of Stack Overflow and GitHub issues trying to figure out the best combination there. Fortunately, I live right near one of, that one Yaroslav guy, so he helps out quite a bit. This is a cool utility. It's this benchmark thing, and you give it, again, the like inputs, and give it the types there, this kind of a weird interface, and then give it the output, which is our add operation. And it's just going to send a whole bunch of like random values through it. And then it'll actually output, if we run this, oh yeah, we didn't actually create, or I haven't created this file yet, but if you did all these like notebooks, yeah, you would have built that. And then here's that signature def stuff. Here's our save model builder, which is the way to prepare it for serving. One thing to note, this clear devices, yes, I get asked this a lot. One thing to note, when you train your model, you are like likely going to mix CPUs, GPUs, TPUs, whatever. When you serve your model, that is typically a very different hardware spec than what you trained on. So right now, given the current state of things, what would typically happen is you would train on a more general purpose type of chip, like a GPU. You would then switch over and serve on a very low power, super highly optimized matrix multiply forward prop, right? And that would be like a TPU. Or you would specifically target those tensor cores within your GPU. And so one thing that you like probably, yes, almost always want to do is clear the devices when you export or do the save model builder and then export it, save it. You want to specify clear devices. I believe this is set to true by default because really those device mappings don't matter at serving time. And because you're like pretty much like guaranteed that you'll be running on different hardware when you're serving, because the profiles of the use cases are like much different. You would clear those devices, and then when you run TensorFlow serving, you have to build the GPU version from source. You can't just pip install that. The CPU version, it's now super easy to like pip install, but the GPU version is not. Yeah, so we have it running here inside of this Docker image, but you would clear the device, and then TensorFlow serving will use the fastest possible mechanism to create those predictions, to satisfy those predictions. And so there's a lot of people that ask, how do I know if TensorFlow serving or TensorFlow is using my GPU? And really the best way is to, in this very, very first notebook up here, we didn't actually do it because of time, but you can, where is it? There's a watch command within like Linux here, where we can actually watch Nvidia SMI. And so, yeah, every second that will update. You can actually shorten it down to like 0.5. And if we put that into a window down here, then we can run I'm just going to restart there. And we see it, blipping a little bit here. See how it allocated all the RAM? See it like blip down there, 5%. So 18%, that was actually pretty good. Not much more going on there. Let's do the XLA one. There's not a very easy way to do a run all within JupiterLab. I don't know why. Yeah, so we saw it blip a little bit there. And then deploying, I don't know if I have this all set up, but when you deploy it, actually TensorFlow serving, when it starts up, will output a bunch of stuff here. Let me see, where do we actually start up? Oops. Now, I think it's already running, right? Oh, no, it's not. Okay. So when it starts up, it should acknowledge, oh yeah, it's not finding that model. Fully optimized because I haven't fully optimized it, but it will actually say, you know, found device 0, that kind of thing for the GPU. Okay. Also, to keep an eye on the temperature is pretty fun. If it's getting warm, it's doing work. Is TensorFlow Lite using GPU on iOS? I don't know for sure. I don't know too much about TensorFlow Lite. I know more about the TF compile stuff. I missed a session this week on Core ML by Apple. So that might have given me a hint. There was not much Apple Google like collaboration, it seemed. So my hunch is no. It would require, I'm trying to think how that would even, it would like so someone would have to come into that layer, and I'm just trying to think if there's any LLVM support. Yes, I don't think so, Stan. Let me see a couple other questions. Use Keras. Yeah, so I would definitely use Keras starting today with new like projects. I've not really, it's either the estimator API or Keras. I know that they can like work together because there's ways to create. But yeah, I mean, pretty much that's the standard. Yeah, everyone. So Keras is a higher level API, sits on top of like these APIs. And there was always a question as to which higher level API was going to win out. And Google hired the creator of Keras, who I literally bumped into about 2 days ago. And I was very starstruck. It was like seeing Tom Cruise. So yeah, he now works for Google, and he's like the main committer guy behind Keras. Yeah, definitely use that. Any options, TensorFlow, to develop a model using time-dependent features, distributed. So I mean, are you talking about like, yeah, so the question is about to develop a model with time-dependent features and then distributed. What's the actual question itself? The options. I mean, there's like definitely RNN support. If you're talking about streaming RNN support, distributed training mode. Cluster. Yeah, I mean, there's definitely distributed training with recurrent neural networks. That's huge. Is there a cluster you can try the notebook after you terminate the current one? The community edition, so let's see. Community.pipeline.ai. You can log in with your GitHub account, whatever, has a GPU behind it. The XLA stuff is not turned on that build, mainly because I just haven't gotten around to it. But you could certainly run the CPU, the GPU, you could do, you could pretty much do everything except the XLA stuff. I don't know too much about that, the scheduling models. GPU desktop. Oh, yeah, this question comes up a lot about how do I get this working on my home GPU? Yeah, again, we can't support that. Suggestions on how to get, I mean, you can look at the instructions, which I'll paste in here again for how to get this going on the cloud and then just back into it from there. Yeah, even thinking about like getting this working on a standalone machine just makes me cringe. So if you start here, click. Yeah, I'll paste it in. Even these instructions are a bit shabby from time to time just because of the different. One thing to note, if you are trying to get this Docker image working locally, or yes, anywhere, is right, like to again, make sure that you pin to a specific version of the operating system. When you provision the node from right, like Google, for example, you need to say, so here's an example. If you notice in here, I'm specifying the accelerator. That's easy breezy. You have to pin to a particular image of Ubuntu. So don't just rely on the default Ubuntu, because it will be different. Even if it's just a couple days old, it's going to be different. So you physically pin yourself to a particular version. And I actually don't know the command line to do that within Amazon, because I don't have Amazon scripted as well as I do Google, because I tend to use Google more. It's just a little bit cheaper on the GPUs and stuff. And so there's that. You need NVIDIA SMI. Or sorry, like you need the NVIDIA Docker project. That'll wrap Docker. And the other thing is just, you know, pray that the GPU gods are working with you. The one problem with your home GPU is depending on the version. So these, let me show you the builds. Where is it here? I'm going to pull up the Docker image that powers. So again, this is not very reusable because it is very specific. Oh, actually and it's still using the old flux capacitor one. So hang on a sec here. Where is it? It's under Tensorflow, I think. So this particular Docker image will highlight a lot of the pain. This is actually based on the developments. So like keep in mind that I had to get both TensorFlow serving and TensorFlow to build from source for the GPU. For CPU, this is a lot easier, and also to turn on XLA and all that stuff, you have to set these flags. So actually, I first build TensorFlow serving, then I build TensorFlow. But one thing to note about your own personal GPU is Well, A, if it's not the Nvidia GPU, you have no chance to get this to work. And not unless you have the rare MacBook from, I think, 2012 that had the Nvidia GPU, which actually TensorFlow doesn't even support that anymore. They did for the first couple years of TensorFlow, and they've dropped support. But you have to look up your GPU. So we're on the K80, and in CUDA speak, this is a compute capability of 3.7. So I just put it in these comments because I found myself looking this up all the time. The Amazon G2 instances are these goofy K520s, 3.5. I'll get to what these mean here in a sec. Tesla, which is G3, which is what the community edition uses, is 5.2. K80 is 3.7. The P100 is 6.0. I think the V100 is like 6.2 or something. I don't think they're at 7.0. But what this means is you have to have built for the particular like compute capability. So when you build TensorFlow from source, you have to say, I want to support, these like various ones. Compute capabilities always go up, right? The number always goes up. And if you see like a 6.1, something like that, that's usually the consumer version of the original like data center version. That's just kind of classically how it's been, or slight variants. They've like disabled certain features, and so the compute capability goes down. The like numbering goes up, but yeah, and you can look up NVIDIA compute capability, and if I want to look up 6.0, there's like a whole chart. Actually, I think even like Wikipedia had it pretty well. Like there's a chart that I found that kind of outlines everything based on compute. In fact, I think it was in one of my slides early on. Is it from here? Yeah, so here's compute capability. What you would do is search for your, oh yeah, so they are up to 7.0 for the Volta. So Titan V, that's the $3,000 card that just came out. And this is just saying the model and the compute capability, but the actual capabilities are listed elsewhere. Oh yeah, here. So things like 16-bit, the half precision, 16-bit floating is since 5.3, actually. Now TensorFlow, earlier versions of oh, and there's one goofy parameter that you have to set within TensorFlow. Let me find this. Where is it here? Yeah. Yes, it was on the slide here. So this is in reference to the 16-bit floating point add, multiply, multiply, add. So since 5.3, number of native instruction, number of results per clock cycle per multiprocessor. So 128. So actually, yeah, this seems to have gone down there. 6.2. And you have to set this FP16 matmul use FP32 compute equals 0. So make sure that that's set in your, yes, actually, I don't even have that set because right now that Docker image is optimized for the K80. I build for other things as well too, just in case other people want to run on different hardware, but anything else here? Yeah, the 1080 Ti, gotcha. Yeah, so you should be okay. Just get CUDA 8, CUDA 8, cuDNN 5. I believe, or 6. Make sure, yeah, those, oh, that's actually that would come from the toolkit, I think. Yeah. I don't know, man. Good luck. Yes. Anything else, guys? Thanks for sticking around an hour later. Put my email in here. And thanks for spending time. Talk soon, guys.